Yeah, hello all. So, welcome to the fourth day of the faculty development program on VLSI design using eSim and Open PDKs. So, uh, on last 3 days were wonderful, and we looked into a lot of things. We had different speakers from different backgrounds. So yesterday, Vipul Sharma talked about Sky 130 PDK, and there was a hands-on demo by the eSIM team. Then in the morning, we had a wonderful session on nodal analysis by Professor Rakesh Sinha. So this is the final day, and So Professor Maurina Ghosh from Triple IT Guwahati will be talking on EDA tools. Then I will be demoing on eSIM, a hands-on session. Basically, a brief of what all tools are there in eSIM, this that. And then Vladek Grevinsky from IHP Germany will be talking on introduction to Open PDKs with IHP, Open PDK and eSIM. And then we will do a hands-on session on IHP Open PDK. And then we will have a conclusion talk by Mrs. Payal Mukherjee from FOSSI. Okay. So introducing Professor Maurina Ghosh. So she's an associate professor at Triple IT Guwahati and currently the HOD in the electronics and communication engineering at Triple IT Guwahati. She did her PhD from ISM Dhanbad, and she is into VLSI signal processing and different other things, as you can see. So welcoming Professor Maurina. Over to you, ma'am.
Thank you for the introduction. So let me share the screen first. Is the screen is visible?
Yes, screen is visible.
Okay.
Yes.
So so before going to the EDA tools,
Excuse me, ma'am.
just
Ma'am, this next slide is getting. Please share the complete screen.
Just no.
This
Just click on display setting. Just click on
display setting,
display setting and duplicate slides.
duplicate slides.
okay. 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 So hello
No,
everyone. So
no,
myself,
now it's
Dr.
not
Maureen
visible.
Mathur.
Not
Yeah,
visible.
now it is visible, right? Okay.
No, not visible. Not visible.
Not visible.
Yeah.
1 second. Now it is visible.
No, ma'am.
No.
Just 1 second. Now it is visible, right?
Not yet. Now it's visible.
Okay. So if I'm going to the slideshow, I think there is a problem. Okay.
Otherwise, you can share it this way only. If it's,
I think that is the better.
yeah, that's
Okay.
better.
Yeah. So hello everyone. So myself, Dr. Maurina Ghosh. So right now I'm the associate professor of Triple IT Guwahati. So my basic research is the analog VLSI design. So before going to the any EDA tools, so just introduction what I have done till now in my research. So today topic of discussion is design of analog signal processing circuits using current mode building blocks. So this is the flow of the presentation. Introductions of ICs. This is very basic things. What is current mode circuits and its basics, different types of current mode ICs, then some literature review, and then after that, how we can design filter, oscillator, inductor, all these things. That's a signal processing circuit using current mode based building blocks. And last, that right now what I'm doing in last 4 or 5 years, that is design of memristors using current mode based building block as well as using MOSFET. So then after conclusion, reference and list of publications. Okay. Now next is what is IC. So we all know that IC is nothing but an integrated chip. So it is basically divided into two sections: analog IC and digital IC. So analog IC two types. One is a voltage mode. That's op-amp is a voltage mode based IC. Another is a current mode based IC like OTRA, CDBA, double C2, triple C2. These all are the current mode based IC. So ICs basically we all know that all the components are fabricated in the single side of the silicon chip. Okay, now what is current mode based IC? So this is basically that is a branch currents of the circuit. Rather, in this here, the information is represented by the branch currents of the circuit rather than the nodal voltages as a voltage mode based circuits. And it is basically following the principle of the translinear. So next I will describe the current meter circuit, then you will understand that what is a current mode based circuits properly. So basic difference I can say in the voltage mode based circuits, your gain bandwidth product is very limited. Like in the if you go for the op-amp 741, the gain bandwidth product is limited to your 1 megahertz. But if you go for the current mode based circuits, your gain bandwidth product is quite high, power consumption is very low, and the circuit structure is simple. We are getting high slew rate. So as we know, that is the this is the basic requirements of any VLSI circuit design. That's a power should be low, speed should be high, and the circuit should be very compact and simple. So all these things actually we are getting in the case of the current mode based ICs, and this is basically following the translinear. So there's a different types of current mode based circuit. That is, it first started with the first generation current mode based, then second generation, then third generation, then there is a different type of current controller is there, and other current mode based circuits, which is right now I will going to describe, that is CDBA, current differencing buffer amplifier, OTA. I think we some persons are familiar with OTA also, operation transconductance amplifier. So OTRA, operation trans resistance amplifier. So these are the different current mode based ICs. So just an introduction, that is what is the basic difference. Like if we go to the block diagram, so this is a simple op amp, that is inverting, non-inverting, and this is your output. And similarly in the current mode based ICs, we are getting this port, X port, Y port, Z and Z port. So these all are not fixed for the other ICs also. Like if it is going for a OT array, the port is changed to N and P and Z. So like this, there is a different ports are there. So if you simply compare, this is slew rate is quite high in this case, and power supply is quite low, and that is tuning capability is there. Frequency range, that is gain bandwidth product, is limited to 1 megahertz for the 741, or you can say simpler op amps. But in the current mode based IC, the gain bandwidth product is quite high, and here it is also commercially available like AD844. So we already tested with in our labs, like we have designed different current mode based circuits, and and from there we can design the different signal processing circuits using AD844 and LT1228. So all these things are commercially available. Okay. Now, next is a fundamental concept of the current mode based IC, that is, it's based on the current meter. So we all know that this is all this concept, but just introduction, like what happened in this case. If we go for a MOSFET based current meter, we all know that this thing, that if we connected this your gate and drain together, then we are getting almost the same current. That is, if you are passing that is whatever the current flowing through this transistor, the same current is passing through this transistor also. So here, that is for the I reference, we are getting VDD minus VGS. So this is a simple equations. Similarly for the Q2 also, and we all know that transistor is always in the saturation region. When we go for the current mirror, or we can say this is a constant current source. So basically MOSFET can act as a constant current source. So in which region? So in it is working as a saturation region. It is working as a constant current source. So if our WL is similar, then whatever the current is flowing through ID2, the same current will flowing through ID1. So we are just copying the current. So this is the NMOS based current mirror, and this is your PMOS based current mirror. Now this one is a current steering circuit. So if a multiple MOSFETs are connected together, or we can say n number of MOSFET are connected together, then we are getting almost similar kinds of current in everywhere. But the condition is the WL ratio should be same. So this is for the another different current steering circuits. Okay. Now this is the different current mode building blocks. So first, this is the from topic where we have where the research is started. So here the different current mode building blocks. So that is first I will describe, that is a AD844, which is a commercially available. So this one, this circuit is commercially available, and the port relationship of this is here in this matrix. If we solve this matrix, we will get the port relationship of the AD844. So AD844 is nothing but a double C2, that is a second generation current conveyor with a buffer, that is called a AD844. Next is another current mode based circuits is like our CDBA. So we have designed here this one, current differencing buffer amplifier. So all these things we can design in the EDA tools. Okay, so and that is, we can give the WL ratio, that PDK if you want to give, so that all these things is possible in the EDA tools. Okay, so here this is your MOS based CDBA circuit, and here we are using 30 number of the transistor and this WL ratio. So initially when we have started, we have done with a 180 nanometer. So right now you can go beyond to that, that is a 90 nanometer, 69 nanometer, 45, 32 nanometer. So we are also working on these things. Okay, and the port relationship of the CDB is given in this matrix. Next is another one, that is I think most of the people are familiar with this one, that is Operation Transconductance Amplifier, that is our OTA. So this is the most based OTA diagram, and this is your aspect ratio. This is the aspect ratio or WL ratio we can see, and this is your that is the our port relationship. This one is the port relationship of the portie, and there is a different port. So just like here, if you go to the CDBA, the ports are P, N are the input ports, and WZs are the output port. Similarly for here, so this one is V1, V2, the voltage we are giving, this plus minus, these are two ports, and O is the output port. So we can make it as a dual output also, O plus, O minus, and V is the bias. Next is here another kind of current mode based building block, that is a voltage differencing buffer amplifier, VDBA. So here VDBA is a this is your P and N, this is a two port, and Z is the output port, and this one is your bias current, and this is your voltage we are giving. So this one is the another diagram of the VDBA. Okay, so this nowadays there's a lot of researcher going on using VDBA based memory state design, like because this is a very you can say there is very less number of transistor we are using. So VDBA is right now going on. Now there is another one, that is a OTRA, Operation Trans Resistance Amplifier. So here if you solve the matrix, what are the relation you are getting? That is VPVN equals to 0, and V naught is equals to RM IP minus IN. So if you solve this equation, so you will get that the port relationship of the OTRA, and this is your this one is your MOS based. So you can also do the BGT based, but as we know that BGT is almost obsoleted, so all of the research is going in the MOS based. So our all research is based on the MOS. This is the WL ratio of your MOSFETs with circuits. Now this is so here I have just told you about the 4-5 type of current mode based circuits, but there is a not 4-5, there is a lot of current mode based circuits, and there's evolutions continuously going on, that how the number of the transistor can be less, and that is for if speed can be increased, or power consumption, how we can make the very low power consumption. Okay, so that's why there is a lot of research is going on. Now first we are going to design, so yeah, that is a quadrature oscillator, quadrature oscillator using current mode based circuit. So here some key findings are there, that is a, so first, what is a quadrature oscillator? That is we are getting two output, two oscillation from the circuit, and there is a phase difference between this two output of the oscillator. So that is a quadrature oscillator. So here some key findings are there. So a lot of research is done in the oscillator based circuits. So later on I will coming on the filters and inverse filter based circuits, and then memristor and mem inductor design. So first let me start it with the designing. This is the one second. Okay, so first is the filter design using current mode based circuit. So so as we all know what is a filter, so there is a two types of filter circuits are there. Filter is basically that is passing some frequency and blocking the other. So there is a five types of filter, we know that, that's low pass, high pass, band pass, all those things, and there's a passive filter and active filter. So basically we are going to design active filters using current mode based circuits. Till now what we have learned in our that is BTech, that is there is only op amp based filters are there, means using active building blocks. We have done only the op amp based design, but right now we will going to design different kind of filters using current mode based building blocks. So this is the types of filter that is we all familiar with. This is the transfer functions of those filters. Okay, now this is a different first order filter design. So this is your op amp based filter design, so I'm not going to this one. So we can directly go to the design of this thing. That is a this is the work done, that is the third order voltage mode band pass filter. So here I show the first design of band pass filter using that is DO triple C2. So why it is a third order filter? So first we need to understand what we are going for a design for the higher order filter. So as we know, when the filter order is increasing, when it is going from the second order to third order, then the sharpness will increase. Okay, and it is acting like a that is ideal filter. So that's why the third order filters. But when we going to design third order filter using op amp based circuits, the circuits is going to be very complicated. So that's why and that is a problem for the designing in the VLSI chips. So that is why we are going for the current mode based circuits design, that is a higher order filter. So here what we have done, so this is the designing part, this one is the designing, and this is the equation. So how we have solved this equation, we have solved this equation using the port relationship that I have already shown you previous slide. That is the using port relationship you can solve the equations of this circuit. So first we need to write down the port relationship, and then we can find out the transfer function of this third order filter. So next is here, this is the another second configuration. This is the this for first, this is the first configuration, and another configuration is this one. And why it is a third order, when we have solved this we are getting x cube. So from here we can understand that this is a third order filter. Now this is your simulation results. So you can do all these things in the EDA tool. Later I will show all these things. So here we are getting the third order filter characteristics. Here it is minus 40 dB per decade, and here is 60 dB per decade. So this is a that is asymmetric. It is not 30-30, it is a 40 and 20. So this is a asymmetric filter. So this is also 20 and 40. This is the second one. And theoretical calculations, that is also impossible in these tools. That is, first we can do the simulation, and for the theoretical calculations we have to calculate this equation. We have to write this equation and we can put into the simulation tool, and then we can plot it them together, so that then you can get the simulation as well as the theoretical result. Next is the that is another filter. So right now why I'm talking about the higher order filter, that's I already told you that higher order filter give you the output characteristics which is closer to the ideal filter. So now this is the next design, that is the fifth order filter using CDBA. Okay, so this is the fifth order filter using CDBA. So here the this one is the basic structure. Okay, this is the CDBA structure, and this is that already I told you that this one is the one second. uh, this is the basic CDBA structure, and this is the port relationship of the CDBA. So this is a current mode based building block, and using this we have designed using this we have designed this fifth order filter. So these are the different types of impedances which is shown here. Now for the low pass filter, we just want to replace this with this YP, have to replace with this connection. And yes, this one for the YN we have to replace with this. So this is, here we are using quite large number of the passive component. But if you see that if you're going to design a fifth order filter using only op amp based circuits, so it will be taking more components, like but if you're going for a, here the main motive is that using only one CDBA we are designing a fifth order filter. So this is the equation which we have solved from the CDBA port relationship, and this is the different filter functions. So if mathematically we have solved this numerator denominator, then we can get the filter characteristics like this one. So this is your cutoff frequency and quality factor. We are getting from this, after solving this, we are getting the quality factor, cutoff frequency of this filter. So for the previous filter also I have done that is cutoff frequency, quality factor, that is not shown in the slide. Okay, now this is the another calculation which we have done, that is the sensitivity calculation. Sensitivity is basically when the components variation is there, that resistance, capacitance, all these variations is there, then how much it will affect the quality factor and the cutoff frequency, that is actually the determine our sensitivity. So theoretically we expect the as low sensitivity, but here also if we solve the equation we are getting that is minus 1 by 5, so it is quite low sensitivity. Now this is, all these things are done in the tool, simulation tool. So here this is the output of the low pass filter. So here if you check, there is a three output we are getting. So three is basically first is a theoretical output, that I have already shown you the is equation. So if we solve this equation and put in the simulation, the it is automatically give you the output characteristics. So one is the theoretical output, another is the simulated output. For the simulated output, this is the circuit, and we have to put the different values of those R and C. Then we are getting the simulated output for a particular cutoff frequency. So first we need to fix the particular cutoff frequency, and then we can get the simulated output. And another is the experimental output. So as I told you that using AD844 we can construct CDBA circuit as well as the OTRA circuit also. So here the picture is there, that using this AD844 we can create a CDBA circuit as well as OTRA circuit. So for the in the lab we have done this experiment, and the experimental result also shown here. So this is the low pass output characteristics, this is your high pass output characteristics, and this one is the band pass output characteristics. Now this is your THD, that is total harmonic distortion we have calculated. So all these things, all these simulations are possible in the EDA tools. That is total harmonic distortion to your output characteristics, frequency versus gain, and the theoretical calculations, everything is possible. Now next is a, this is a comparison table of the proposed work with the earlier reported work. So if we go to the comparison, so if we check, that is this is the order of the filter. So there is no fifth order filter is designed till now. So we have designed a fifth order filter with only one active component. So that active component is basically the CDBA. That's using only one active component we can able to design the fifth order filter. Now here if you check from the comparison table, so previously only third order, second order design is there. So few third order design is there, but most of the cases there is only second order design is there. And the number of the active building blocks, if it is using CDB also, that is also very high. But in the case of our design, we have done the fifth order filter using only one CDBA block. And here the number of the passive components, if you compare with the number of the passive component, yes, our passive component count is high. But in our next that is next future work is how to reduce the passive component and make the active component as it is, but how we can modify the design so we can reduce the passive component. And this all this most of the design is done using BJT, but few are in the CMOS also. So and we have done our design is 180 nanometer CMOS technology. So if you go to the power dissipation, so power dissipation is also quite low, that is 0.821 milliwatt. And that is one interesting part is that the number of the transistor is very low, it is 14. So if you compare with all these things, if you go for the third order only single all pass filter, then also the number of the transistor is 144. So here the number of the transistor is quite low, that is a 14. So in the case of the VLSI design, it quite helps. And the supply voltage is quite low, that is 0.6 volt. So and that is all the components are grounded or virtually grounded. So that is one of the advantage of the circuits, that that passive components either it is grounded or virtually grounded. It's not the floating passive components are present. So this is the another this is the design. Now the layout design, post layout, pre layout simulations, all these things, and this is already possible in the ADA. So first what we have to do, that if we going to design any kind of circuits, let's say it is a current mode based circuits or any voltage mode based circuit, so first we need to do that simulation. So before the simulation we have find out the theoretical results, and then we have done that part into the simulation. And after that simulation, if the simulation is coming properly, then we have to check with the theoretical results. And then that is layout, post layout simulations and pre layout simulations. So this is the way what we have done. Next is a uh, design of the quadrature oscillator using CDBA. So design of quadrature oscillator using CDBA. So first design that is a CDBA based filter design. Now next is a CDBA based quadrature oscillator design. So here the three type of circuit diagram we have proposed. That is this is the first diagram, this one second, and this is the third. And all these things are the third order quadrature oscillator. Okay, so why it is a quadrature oscillator? Because we are getting the two outputs and there is a phase shift between the output is oscillation is 90 degree. So this is the V01, the voltage output we are taking from here. Another is the V02, the voltage of the uh, another block. Okay, and resistance, capacitance are there, and they are grounded or virtually grounded. So why I'm telling this is a virtually grounded? So if you go to the port relationship of the CDB and or VDBA, these two terminals VPVN is nearly zero. So that's why I'm telling this is a virtually grounded. So when we are going to solve the equations also, then we have to take that VPVN equals to zero. So that's why it is a virtually grounded. So let's go to the design. Okay, so after designing this thing, what is the next step? That we have to solve the equations. So how we can solve the equations, I already told you. So before if you want to solve any kind of equation, so you have to means know what is the port relationship of that particular block. So for a CDBA, the port relations is different from the OTRA, and the OTRA port relations is also different from the double C2, triple C2. So each and every current mode building block, we should know what should be the port relationship. Then we can solve the circuit properly. So that port relationship and resistance capacitance, if we use, then we are getting this equations. Okay, so this is the equation for the three types of oscillator circuit. So from here we have to find out the oscillation frequency and condition of the oscillation. So we already know how we can find the condition of the oscillation and oscillation frequency. So this is the oscillation frequency and this is the condition of the oscillation. Next is the this is that part is continuing. So I will show you the simulations results later on. So next design is fourth order quadrature oscillator. So here also fourth order quadrature oscillator, three types of the oscillator output we are getting. So here why it is a third order, because x cube is there. So similarly for the fourth order, if you check another, if you check the equation, this is s to the power 4 is coming. So here also, so what we have done in this diagram, say or in this simulation circuit, that we are using the MOSFET also for the switching purpose. So from the one circuit, if we switch, like if the switch S1, S2, and S3 all are the on, S4 all are the on, then what happened? You are getting the first order. You are getting a first type of fourth order quadrature oscillator circuit. Similarly for the others also, which switch should be open. So depending upon that, we are getting the different types of oscillation circuits. Now this is the analysis. This is the analysis of the fourth order quadrature oscillator circuit. So same analysis, like we have to take the port relationship, and from that port relationship we have to solve the circuit. So here is the oscillation frequency and the condition of the oscillation. So the sensitivity analysis, so as I already told you, that this is a one of the major component, like how the resistance and capacitance, this passive component affecting your cutoff frequency, and here in this case the condition of the oscillation or frequency of the oscillation. So how this are affecting the frequency of the oscillation. So these are the some equations we have find out. Now these all are the simulations results for the oscillator circuit. So this one is the simulation for the first circuit. This is the for the second. This is for the third. And if we zoom this thing, then we are getting this type of output. So here is a 2 voltage output you are getting, that is V01 and V02. And if we find out what is the difference of this angles, it is almost coming the 90-degree difference. So that's why it is a quadrature oscillator. Now this is another different types of the simulations results, and this is all the litigious patterns we are getting. So all this done in the done using the EDA tools, everything. Okay. Now this is your that is a total harmonic distortion. So there is, if you go to your tools, so there is a box that how we can calculate the total harmonic distortion, what should be the number of the harmonics. So generally we are taking 10 number of the harmonics to calculate the total harmonic distortion. Okay. So this one, this is the temperature variation. So this is for the first diagram. So if you vary the temperature, then how your frequency of how your oscillation output is varying. So this is done for minus 20 degree to 100 degree centigrade. Okay. Now this is some of the experimental results. So as I told you, that is before any fabrication of the chip. So what we have done, that is first the simulation, and simulation pre-layout and post-layout part is there, and also there is a lab verification is there. So lab verification is basically done with the available components like 8844, and another thing, that's 8844 is a BJT based component. So for the lab verification we are doing this thing, but for if you want to develop a chip, then that is we have to go to the different institutions where they will help us to develop the chips. So we have to give the GDS file, and then according to that chip will be developed. So here is the experimental result we have done. So this is the in the lab, in the DSO we have done this experimental result. So it is showing that litigious pattern is also coming properly. So this is for all the experiments are done for all the circuits, but I think here it is shown only for one. Now this is the layout design. This is the layout we have done for the only for the, this is for the first circuit and this is for the second circuit. Okay. Now this is some the application of the oscillator. So designing nowadays, so when we have written any paper, so only designing of the circuits it's not enough. So that we have to show some proper applications, like where which circuit we have designed, where it is useful, or it is useful in the communication system or any digital system, whatever. But we have to show something that this is our application of the proposed circuit. So that's why here we have used our oscillator in the quadrature amplitude modulation circuit. So this is the transmitter side and this is the receiver side, and here this is, you all know, this is the general diagram, but here we have used our proposed quadrature oscillator circuit. So that already I show you, that is a third order and fourth order proposed quadrature oscillator circuit, and we are taking this type of outputs. Okay, now this is the outputs we are getting, the simulations results we are getting. Okay, next is the your comparison of the current mode based oscillator circuit. This is the comparison table, like that is a how the oscillator circuits are designed, which technology they are using, that is the number of the transistor count. So here if you check, so that another thing, that is our design is giving you a less number of the transistor count. So if you compare with this one, they are also taking 24 number of the transistor count, but here our 28, but the block is, the active block is here is 3 OTA they are using, and we are using only 2 CDBA. So that is the another thing. Okay, now this is the number of the resistance and capacitance counts are there, and electronic controllability. So most of the circuit don't have that electronic controllability. So what is that controllability is basically that is, if you change this any of these values, then you can control the frequency of oscillations. Similarly here, if you're changing any values, then you can control the condition of the oscillation. So that is the controllability is there, so which is not giving the which is we are not getting from the previous circuits. And experimental verification and layout design, everything is done in our circuits. um, this is the another comparison table, which is based on the frequency of oscillation, supply voltage THD, sensitivity of a proposed oscillator with respect to RNC and power consumption. So if you check, so the proposed circuit is a quite low power consumption, that is almost 0.71 milliwatt. Now next is the design. So two types of designing is done, that is one is the filter circuit design, another is the oscillator design. So third I will show you, that is a inductance design. So in why we require inductance, that is in some circuits we use inductance, but as we know at it, inductance are bulky, and it is a magnetic core is there. So for the VLSI based design we cannot use those inductors. So that's why we are proposing for the active inductors, means output of the circuit is just, it is just acting like an inductor, but it is active, means it is based on the MOSFET only. So that's why this is the active inductor. Now what is the difference between the positive inductor and negative inductor? This is just a very simple, that is impedance here is minus JWL, magnitude is same, phase is minus 90-degree phase shift. Means if the current and voltage difference in the positive inductor is 90 degrees, so in this case negative inductance is minus 90-degree. It's leading and lagging difference is there. So this is the first design using OTRA. So already I told you about the OTRA is another building block like CDBA, but the port relationship is quite different. That is here VPVN is also virtually grounded and only one output port is there. So if you go to the CDBA, there is a two output port is there, but if you go to the OTRA, there is only one output port is there. So this is our first proposed structure of OTRA, and using this, so this circuit is available, and yeah, we have put at our resistance capacitor such a way that it should give a inductor output. So here, so this is the mathematical calculations. So if this yn is in by vn, so this is the mathematical calculation we have got from this circuit. And if we, so if the following condition is met, then we are getting this inductance value. So this is the following condition, then the inductance value is this one. And this is the simulations results. So as like previous what we have done, this is the another simulation we have done in the EDA tools. Right, this is the theoretical version. This dotted version is the simulation version. This is the theoretical version. So there is some difference in the theoretical simulation. If we go to here also, there is little bit of difference in the high frequency range. So as there is a lot of parasitic components are present, so that's why there is a difference in this simulation theoretical. They are not properly matched. So we have done for -2 millihenry this output, and now this is the showing the property of the negative inductance. So here current and voltage difference is there. This is the voltage and this is the current difference. Similarly, if we give this your current and voltage like this, so whatever the EDA tools are using, there is a you can change it to, means you can give the input like whatever you want. It's not like that every time you have to give the sinusoidal input or like this. If you want a triangular or square input, you can give it to like that. So here we have giving this input as a square and we are getting this triangular output. Okay, so now the hardware verification. So as I told you that using 28844, if you construct the CDBA, so using 28844, you can also construct the OTRA also. So here using this, we have done done our experimental verification in the lab, and this is the output results. Okay. Now, application here, I have shown a very simple application. Like if you're giving a 2 millihenry, uh, simulate 2 millihenry positive inductor, and our proposed circuit is -2 millihenry negative inductor. So they will be cut down to each other, and the circuit will be a total resistive one. So here the circuit is a resistive circuit. That's we are getting after simulation. And if we are giving a 10 millihenry positive inductor here, so 10 minus 2 8 millihenry we are getting. So all this calculate, this is also another output which is showing that if you are using 10 millihenry positive inductors, then what should be the output. Now this is your another one, that is your that is the TST calculation. TST calculation we have done, and this is the output we can show here. Okay, now next one is the this topic that is right now I'm working on this, that is the memristor design, or this is, you can say this is a new component which is invented by the Professor Leon Chua in 1971. But like in next this 50 years, it's not, research is not means done so much on this. But right now there's a lot of design, a lot of research is going on in these memristors. And memristor is one of the key component for the neuromorphic circuit design. So we all familiar with that neuromorphic is an emerging technology. So nowadays for the AI and all those things, a neuromorphic is an emerging technology, and for their memristor design is one of the key component. So first, let me just tell you what about the memristor. So memristor is nothing but a memory with a register. So here previously, if we go for the relationship between all these things, there is a relationship between V and I, VQ, and I and phi. But there is no direct relationship between the phi and Q. There is a missing link is there always. So that missing link is basically the that is a memristor circuit. So here there is a, if you go to the characteristics, so this is the R, this is your capacitor, and this is your inductor. Only the phase difference is there between the inductor capacitor. But if we go to the memristor design, this is the pinch hysteresis curve is we are getting from the memristor circuit. Why it is a pinch hysteresis? Because from the, it is going from 0 0. Okay, so this is pinch at this point. So this is the output of the memristor characteristics. Now this is the memristor different features. So itself, this memristor design will take another 1 hour. So I'm not going too much of details as there is a very less time. So just the introduction that what we have done in the memristor design. So this is the current voltage curve, this is the current curve, and this is the voltage curve, and how we can plot it, this all these curves in the EDA tool. So if we increase the frequency, if you increase the frequency, if you check omega 3, omega 2, omega 1, what happened, the loop area. So this is basically the loop area of the memristor which is going to be squeezed. Okay, So this is the, and there is a theoretical validation also, that why this loop area is decreasing. So here, so basically memristor is nothing but a memory with a resistance. Like suppose if we that it is a basically a non-volatile memory. So if you switch off the device also, when we have started, then the resistance will remember from where you have end. So that's why it is a non-volatile property, and that is why it is one of the key component of the neuromorphic circuit design. So this is some the mathematical calculations are there using Ohm's law. It's a very simple calculation I have shown. So this is the your charge control memristor. There's a two types of memristor is there. One is the charge control memristor and there's a flux control memristor. So these are the some equations of charge control and flux control memristors. Okay. Now, when we have started the memristor design, so we have started with the current mode bit building block, and right now we are now proposing the memristor using only one MOSFET also. So recently, our one paper is published in IEEE TCAD. So here, in that design, we have used only two MOSFETs for designing a memristor circuits. And another paper is also in the progress, that is the memristor design using only one MOSFET. So, but when we have started that, we have designed using a current mode based circuits, and here we have used quite large number of transistors. But right now, when the research is going on, the number of the transistors are reducing quite abruptly. Now, here the first design, this one is the grounded memristor. So this is the memristor symbol. This one is the memristor symbol. So this is a grounded memristor, and this one is the floating memristor. So you can check V1, V2, two voltages are there, and this is one voltage is grounded. So grounded or floating memristor is there. So other than memristor, there is another circuit also, mem inductor, main capacitor is also present. So we have also worked on the mem inductor. So this paper is published in MWCAS, and so just the circuit I have shown here. This is some mathematical equations, mathematical analysis we have done in the using this circuit. So as I already told you, so OTRA has a fixed port relationship, VDBA also have some fixed port relationship. So using those port relationship, if we design the circuit, then you can get this type of mathematical equation. Another interesting part is there is no passive component are using. Okay, so right now what we are trying to do, that we want to reduce all, or you can say we want to eliminate all the passive components, so as it is helpful for the monolithic IC integration. So that's why we want to reduce all the passive components. So here only one MOS C capacitance we are using. Other than, you can check, there is no passive components at use. Okay. Now this is the this one is the mathematical equations of the memristor circuits. This is the mathematicals, and this one is the simulations. So this is the simulation, that is the voltage and current difference. And if we plot this thing, so first we need to plot this difference. That is a this is the output. When we giving the input as a voltage, then what should be the output as a current? So output current is just shifted. So there is a reason, if we go to the actual property of the memristor, which is the memristor design is done using TiO2, then you can understand why there is a shifting in the current and voltage. So I'm not going for that explanation. I'm just giving you the overall ideas and what we are right now, what we are doing. So this is the different pinch hysteresis curve we are getting. And if you check, as I already told you, that when we are increasing the number, increase the frequency, okay, so at some time the loop area, this is the loop area, is going to decrease, and after certain frequency it is not acting like a memristor. It's simple, it is giving a straight line, so it loses its property. So that is another important thing we right now we are looking, like we have to increase the frequency range. So that's last paper we have published, the frequency range is up to 3 gigahertz using two MOSFET. What the memristor design we have done, that frequency range, it's working up to 3 gigahertz. Okay, so but this paper is the frequency is 5 megahertz only. So this is the This one is the output for the grounded memristor. This is the output for the floating memristors, and this is the temperature variation. If you do the temperature variation, what should be the pinch hysteresis? So as it is a stable circuit, so there is a very means your pinch hysteresis loop is not vary as much as with the temperature. So we have started with minus 20 degrees centigrade to 100 degrees centigrade. So all these things are possible in your tools, and that is slow, so fast. These things we have also done. So this is some the semiconductor properties, so all these things it's possible in your tools. Okay, now this is the capacitance variation. So if we vary the capacitance value, so I told you in our design there's only one MOS capacitance is there. So if we change the MOS capacitance value, then how your pinch resistance loop will change, that is shown here. Okay, and this is the non-volatility test we have done. So I told you that non-volatility test means if you switch off the device also, the transistor, or you can say your device will remember what will be the last value. So this is some non-volatility test. And this is another applications, that is a floating parallel series. If we make two memristor in the series connection, then what will be the output? If we make two memristor in the parallel connection, what should be the output? So this is the some results. Now this is the experimental result we have done. Okay, so CA3080 is basically the OTA IC, and this is for the VTBA we require LM356 and 13080. So this part is constructed a VDBA part, and this part is constructed as a OTA part. If we construct all these things together, then we are getting our simulated circuit diagram. Then so we all these things we have put it in the breadboard, and the output we have checked in the DSO. So this is the pinch hysteresis we are getting. So it is theoretical, as simulations it is working up to the 5 megahertz, but in the simulations it's working 3.6, and after that it's losing the property of the memristor. This is the layout versions. This is the effective area of the layout, and then this is the comparison of the current mode with different types of memristor circuits. So if you check, there's a lot of researchers going on nowadays. So here also the important thing, the number of the transistor count. So in our case also, if you check, the number of the transistor count is 25. It's less than any other. And electron tunability is there. We have done it with 180 nanometer CMOS, and the power supply is quite low, and the maximum frequency range is 5 megahertz. So that is, we are trying to improve the frequency range of the memristor circuit. Now this is the application, that is in the how we can use the memristor in the BFSK modulation. So this is the simple BFSK modulation circuit, and here in the place we have removed the resistance and we have introduced our memristor. So this is the symbol of the memristor, and the internal circuit diagram our proposed in our proposed memristor circuit, and then we are getting some of the outputs. Okay, so this is only one design of memristor I have shown. So recently we have worked in another in lot of memristor circuits. So one of our paper that is using three transistor based memristor circuit is published in the IEEE electron devices, and the this paper is published in the IEEE TCAT, this one. And another we have proposed, I just told you that in 2026 we have just published another memristor circuit that is using only two MOSFETs, how we can design the memristor, and that is also published in the IEEE TCAT. Okay, and this is some references. This is some references. This is the list of publications. Okay, so only journals are there. Thank you. Okay. Do you have any questions?
Yeah, thank you. Hello, am I audible?
Yeah, you are audible.
Yeah, yeah, audience. So, thank you, Professor Molina, for the wonderful talk. Any questions? Audience, any questions?
So if anybody wants to continue the research in this domain, that is a memory star design or neuromorphic computing, so you can contact me. We also have a PhD position open, so you can go to the Triple IT website also, and or if you want to do the PhD full time or part time, so you can contact me regarding this. So uh,
Yeah, any questions from the audience? Can you send contact details, ma'am?
contact details, actually I've just forgot to write here, so it is given in the Triple IT website, you can check there. uh, or my mail ID is morina, mourina @triple-itg.ac.in. Okay, so I think there's no questions. Thank you.
Yeah, okay. Thank
Oh,
you, Professor Marina.
thank you for the call.
Yeah,
Thank
for
you.
the wonderful talk
Mm,
on EDA tools and
thank you.
everything. I will share. Just give me a moment. I will share her mail ID. Yeah, this is the mail ID. Okay. Okay. So some audience opinion. All circuits, Madam discussed, can we do in eSIM? Yeah, most of them can be done in eSIM. Yep. Some of the recent ICs, like those of analog devices, which she has shown, are being built by our interns. Yesterday, we were a talk about sub-circuit building. So our interns are developing those circuits. Okay. Anyone else? Any questions? So today's session is like, I would like to know what is your opinion, what you want to learn today. Any message? I want to just know some of your opinions. Hello, professors. Are you all awake? Message something in the chat box. Hello. Anyone? No one? Attendance link you will get, but what do you want to learn in today's session? Anyone? Okay. Problem statements. I see. Attendance link. By the way. Yeah. Other people? Anyone wants to say something? New libraries will be added to eSIM. Yeah, obviously. So some interns are working on them. We have 100 interns currently, as I said. Many of them are working on adding new libraries to eSIM, new IC libraries. Some of the libraries which Professor Maureen Ghosh talked about, those are also getting added. Anyone else? Yeah. Thank you. Thank you, Dr. Chandra. Okay. So what are you expecting today? Today's hands-on session? Anyone? Yeah, mediator is something interesting, definitely. Some of the terms even I heard for the first time. Um, Anything else?
Sumanta,
Ah,
there is a background noise from your side.
still background noise. Now,
Same, same. Okay.
okay, just let me check. Hello, Deepak. Now,
Ah, it's better now.
yeah. Mixed signal circuits. Yeah, good topic. Thank you. Thank you for commenting, Professor Kalpana. Anyone else? Similar kind of responses I want to see over the chat box. Anyone else? I would like to see some more responses from the audience to ensure that you're listening to me. Okay, some likes or something. It's live streamed over YouTube, so you can see the recording over there. Okay. Okay, then I will show some more interesting features of eSIM maybe in today's session. Okay, so give me some time. I'm just setting up something. Okay, so I'm sharing my screen. Lot of explanation in another to intro to memory star. Okay, nice. Yeah, yeah. Vinash, Professor Vinash. Yeah. Do you want to say anything? Anyone else? Anything? Any courses recommended for courses for learning eSIM? Spoken tutorial available. Videos are available. Also, there are we are also creating some tutorials, so those will be available soon. Karthikeyan. Anyone else? And for whatever Professor Maureen Ghosh said, you can go to the website and look into her profile and IEEE profile and check check for those papers. This recording is live streamed. If in case you have doubts, so feel free to check it once again there. And in case of anything, just feel free to mail us. Okay, Karthikeyan. Anyone else? Anything? Okay, then let me start with today's session. How many of you have started eSIM on their laptops, PCs, whatever, computers? For the eSIM software, as of now, KiCad 10 has come. Will the software be updated to utilize the new version? If so, what would be the issue that would be faced while development? Yeah, nice question, Tanisk. In fact, we are facing issues with KiCad development as the older versions of KiCad have been deprecated. So yeah, I mean there are a group of interns who are trying to bypass the circuit this export netlist step, which we have seen in the Ubuntu version. So yeah, So these are the developmental issues. We are also trying to have a UI, but it's a lot of work. So we need interns, software development interns, CC interns for those. Yeah, those working in uh, core software development, they can UI development and all, and help us. What is internship criteria for students from FOSSI? So we already have talked about internship. We have some screening tasks which you need to check. You need to sign into our portal. Sorry, check out our portal. So currently the summer internship is going on. Next month we will be advertising for the semester long internship, so stay tuned for the semester long internship portal. And yeah, so they have some screening tasks which can be solved if the students pay some attention and try it out. So it's not that straightforward that you can ask AI and get the answers, but yeah, you need to pay. You need to work on them, and you will definitely qualify those screening tests. And AI cannot help always in this screening tests, and yeah, you can get through. And after doing the screening tests, once you are selected, we will mail you. So yeah, summer fellowships we do accept some people from offline to the IIT Bombay campus, and in the winter internships and semester long internships, we also take different other. These are online internships basically. Yeah, Vivek. I hope this solves your query. Nagendra, Professor Nagendra, hi. Could you please let me know if there are any upcoming FDPs related to networking or communication? Yeah, so from FOSSI, we are not conducting an FDP on networking and communication, but all around there can be one. So please check on social media platforms. Okay, so any questions related to eSIM? What I want to demo, what you want to know about eSIM, some more features or something like that. Otherwise, shall I continue with the demo? Yeah, some thumbs up or something, hands up or something, some reaction, some reaction. Just 1 minute. Okay, nice. I'm just so I hope my eSIM window is visible. Let's close all the tabs. Oh, yeah. And this is our welcome tab, our favorite tab that ensures that eSIM is working fine. Okay. So now, so what are the yesterday talked about model editor? Okay. So I hope any doubts related to model editor. Did you all try at your in the meanwhile evening time? We ended the session yesterday early. So did you try it out? Anyone? Okay, nice. Thumbs up. Okay, okay. Okay, so yeah, model editor. There is diode, BJT, MOS, JFET, IGPT, magnetic core, and different other stuff in model editor. Then sub-circuit. Sub-circuit, you can create a new sub-circuit. You can edit a new sub-circuit. You can even upload a new sub-circuit if you have a file. So in case you don't have a symbol for a sub-circuit, you need to create a symbol as well for the sub-circuit. Okay, and make a chip. So add top level Verilog model. Okay, so Shanti has already explained it to you. So we have edited make a chip IDE. you need to upload a makerchip file, Verilog file, and you can edit it in makerchip IDE, and the top level module already gets added up automatically. Okay, we are improving this UI to make it better as compared to some proprietary tools. So in next release, you will have a better UI, and yeah, so you will see a better UI. So after loading the Verilog file, if there are additional dependency files, you can load them using add dependency files, then add dependency folder. So if you want to remove some already created Verilog model, for example, counter 4-bit, here I've already created, so you can just click on this and it will get removed. There are some lint of commands. So for these are some messages and commands in the terminals related to Verilator. So in order to add, remove some lint of messages, you need to add them here and click on add lint of. In order to remove them, you can just click on this and remove them. Okay, and this is how this is the gist of Makerchip IDE. Any doubts up till now? Hello all. Any doubts? Any queries? I can see 173 people. They meet. Any doubts? Okay, nice. Yeah, so now we didn't explore the NGHDL feature. So let's check this. Just 1 minute. Huh. Sorry for the inconvenience. Yeah, so this is the NGHDL feature, as you can see. Okay, just 1 minute. Again, share this. Yeah, let me share it again. So this is the NGHDL feature. So you can browse for the, so we already have the examples available in FOSSEE, C, FOSSEE, eSIM, NGHDL examples folder. Let's take the PWM example, upload it. Let's see the background processes. Okay, okay. Yeah, so it's done. Okay, I have closed it. Let me do it once again. Browse in GHDL example, PWM decrement, upload. Okay, see the logs that it has been simulated. Sorry, it has the model has been created. So it's a similar kind of model as the what to say, um, as the ngvary folder, ngvary whatever we have done. So let me show you the models generated, how it works. So, however, this is not in the scope, but still. So here is the counter 4-bit NGV. So here all the NGV models are stored in the NG HDL simulator, SRC, XPICE, ICM, NGV. Okay, and after copying this, these things are built in the release ICM, so NGV. Similarly, we have the sorry. Similarly, we have the GHDL. So PWM decrement which we created has been stored over here. cfunc.c is the folder, this is the function which integrates both of them. Okay, and yeah, I mean, so this release again creates the executable for ngSpice, and that gets linked to the ngSpice. So you can refer to the paper which I have shared earlier and study how the linking and all is done. Okay, now yeah, so let me open up the PWM decrement example. eSim examples. So under the examples, search for the nghdl folder over here. Yeah, mix signal, sorry, not nghdl, it's the mix signal folder. And you can input the PWM decremental. So this is already it's a ready-made example. So I will just show you how the things are working. So again, remap symbols, as many of the examples were created in the previous versions. We need to migrate it to the latest version of KiCad. As someone asked, we are definitely trying best to have the latest version of KiCad. But yeah, developmental, there are a lot of challenges. So yeah, we will try to have it, and for that, some of the interns are also working on bypassing the netlist generation step. Okay. So yeah, so this PWM decrement, what I talked about, PWM decrement. So this is the block which got created after I had run the simulation of NGHDL, the NGHDL executable, uh, NGHDL feature, you can say, and we are giving pulse source to the input, and here is the output, and we are feeding the output back, and hence it's a closed loop system. Okay, so yeah, I mean, here the clock is given after the ADC bridge, but it's preferable to give the clock before the ADC bridge. Okay, so I will just shift it. Okay, yeah. Okay, so yeah, I mean, this is the circuit, and we have the op amp to compare, which is here we have the comparator. It's working as a comparator, and it's the 741 op amp, and this filter, RC filter. Okay, so export netlist, put netlist, and it's already saved, so I'm not doing anything. So moving back to KiCad to ngSpice. So start time 0, step time 1, and stop time they have given us 80 milliseconds. And 0, initial value 0, pulse value 5, delay time 10 micro, rest time 10 micro. This is for the clock. Hold time 20 micros, pulse width 0.5 milli, and time period 1 milli. Okay. So this is the ideal thing. In fact, you can have a lower delay time, but don't give the delay time as 0. It's not preferable. Those who have worked in spice, delay time actually cannot be 0. Okay, so give it as small as possible, but not 0. Yeah. Now ngSpice model tab. So this has a lot of things. Add parameters for DAC. So you can change the default out low value. So you want the logic low as 0 volts or something else. Then enter value for out high. So you want the digital output high value as 5 volts or something else. Default are 0 and 5. Then enter value for out ender. This is also one of the parameters. I forgot. Just check the manual ones. Undefined. Sorry. This is the undefined value for output. And this input load. So input load should be as small as possible. So this, as you can see, 10 to the power minus 12. Okay. And rush time is. Rush time is 10 to the power minus 9, and fall time is 10 to the power minus 9. Okay, and ADC, so input low, again 1 volt. So anything below 1 volt will be taken as 0, digital 0. Anything above 2 volts will be taken as input high. You can change this obviously. And rise delay, fall delay. Okay. So this is the advantage of having the Spice model in this whatever we have seen. We have this block is actually the Spice model, and you can play around with these values. And yeah, these are kind of programmable values, so you can play around with this. Yeah, again DAC, ADC. Okay. Yeah. Device modeling, nothing. Sub circuit, you can add the LM741 sub-circuit from here. You can see the list of sub-circuits which are already there in eSIM 2.5, and lot many things are getting added. You can check the repository of eSIM and download many of them. Okay, so okay, so this way you need to add it. Microcontrollers. So yeah, so this is sometimes this. So this is actually the ngSpice model itself. Sometimes it detects in ngSpice model or in the microcontroller. This was made since we many we have made this feature ngHDL and ngVD even for microcontrollers, like uh, kind of you can, if you have the Arduino RTL code for Arduino, there are various repositories over the GitHub available for Arduino microcontroller at Mega 328P, and you can download it and create a ngHDL or ngVary model of the microcontroller, and then have a similar kind of block over here. Okay. Similarly, in the paper we have also talked about RISC-V processor. Then you can try out various things. We even integrated Shakti and Ajit. Okay, so if you need those, just reach out to us. We haven't uploaded it yet. We will do it soon on the GitHub. Okay, as open source licenses. And yeah, so again, the rise delay, fall delay, and input load for this PWM block, you can vary them. So I am not converting it again since this is already done as an example. You want in the space plots? Yes. So let me talk about the VHDL model files, how the simulation works until the simulation is still ongoing. So basically on the back end, it's running through the socket communication. Like ngSpice is communicating with the GHDL through a socket, socket communication, and these were done in C. So yeah, obviously different people in there was some issues. Yes, through the socket communication it was done. Just let me check 1 minute. Just 1 minute. Yeah, okay. So actually, I was trying something on this PC, so something happened. But so I will show another thing until then. We have this Modelica converter as well. So we'll open up for C. So BJT amplifier. This needs to be deleted as earlier. Yeah. So see same examples. BJT amplifier. Or some other examples, 7 floor. Yeah. Okay, and so this Modelica converter is there. So if you want, you can have this netlist and click on convert button. Okay, so once it gets converted so to the Modelica, so open Modelica converter file. So if you refresh this, we'll see this .mo file in this, and when you load it using OM edit option of the Open Modelica, so it it runs fine in the Open Modelica UI. Okay, so I'm not showing the example in the Open Modelica since This is out of the scope, but this is how the Open Modelica interface works, Modelica converter. Okay, and coming to the eSIM converters, so the PSpice to LTSpice converters. So we have convert PSpice library and uh, um, convert PSpice schematic, PSpice LTSpice library and LTSpice schematic. We are planning to have Cadence, similar things for Cadence and other proprietary tools as well. So, for example, I will show you how to convert a LTSpice schematic. So I will browse to the desktop LTSpice to this. Okay, this is a Colpix oscillator example. So yeah, so click on convert LTSpice. Click on OK. Converted successfully. Okay. Now, after it gets converted successfully, you need to go to the location of the folder where the oscillator is located over here, and select the folder over here. And these are the files that, so it generates the .sh file, which is the previous KiCad version again, but it will get loaded properly. Okay, so the map symbols. Okay, close, load without cache. Yeah, placing it over here. And yeah, some parts may not get loaded since it's not completely automated. There may be some mismatches. So this is the updated library. So this is the converted from LTSpice to KiCad. And so as you can see, this is the voltage sources, resistors, and transistors and capacitors. Everything is there in place. So just deleting them. Okay, adding the ground, adding the ground. Okay, so this is the completed circuit. I will generate the netlist. Refreshing. So these are all the 4 project files that you will observe after generating the netlist and generating the netlist here. And yeah, so add the different values. 4.1 is 100. Okay, so adding the library, a JFET library, and diode, and convert. Okay, so now refreshing it once again. So some edits need to be done manually. For example, this the designator for JFET is J in this spice, so we need to change it to J1. Otherwise, rest of the things are fine. Okay. Yep. Some this thing can be removed. Yeah. So some of the things are fine. Now it looks fine. So as you can see, there are some issues with the C1 pad 2. So one is to debug the C1 pad by it's giving the issues and singular matrix over here and check it out. Okay, so this is a homework assignment kind of. You can get this Colpix oscillator example in the LDSpice library. So please do try it out. Okay, and yeah, and I will just show you a list of PCB design examples. So how to do PCB designing in eSIM? For example, this BJT amplifier I have taken. Or let's take the regulator example itself. Okay, map symbol. Okay, close. Okay, so in order to have the PCB designing feature, let's delete these components, the sources and the plots. Okay, now adding input pins.
Sumanta, can you zoom in little one?
Little bit more. Okay.
Yeah, it's fine.
Now adding the footprints. Yeah. So adding the header pins for inputs. Just adding a port for now. Or let's leave it empty. We will add it in the PCB design step itself at the input and the output nodes. Okay, so just run the PCB footprint assignment tool. So taking a vertical, is it? Yeah. Now for diode, diode through hole, horizontal. Okay, now a resistor, horizontal, and 3 pin. And something for the package. And take perhaps BIP. No, it's not BIP. 7812 comes in which package? Let me check once. So TO package. Then out from here. Yeah, USOT. Apply, save schematic and continue. Okay. Okay. Now let's open the PCB editor. Yes. Now we will import the netlist. So this is the PCB editor of KiCad and eSim. Okay. Now importing the netlist. So important step. We need to generate the netlist. We didn't generate the netlist in the previous step. So export netlist. So earlier we did spice netlists whenever we did some simulation, but this time we need to go for KiCad netlist. So export netlist, save. Okay, now go here, import it, load and test netlist. Okay, update PCB. Okay, close. We can see the beautiful components have appeared. Okay, so there are even auto routers and different auto routings, interactive routing settings and all. Okay, then even you can auto place the components. Okay, but you need to define. So I'm not going for the automations right now. We just manually place it one by one, just to show how the things can be done. And there are different plugins. They were also available in eSim. We are also developing some plugins. So just okay. This footprint is I didn't check, so we can even update footprint. This is for a ceramic. I didn't check it. We can go for the axial vertical. Ah, C radial tantalum capacitors. So for now, I am taking one of them just to show. Trade. Yeah, so you need to one needs to check the data sheet of the different components and accordingly design them. Okay. Yeah. Now let's route it. Okay, so there's a crossover over here. So maybe we'll move this footprint a bit. Yeah. Now deleting the earlier route. This is also creating some issues. So yeah, I mean, I'm keeping this field empty. One can even try for the double routes, double layer. Okay, and just I will show how to add the ground plane. So this is the option to add a field zone. So ground. Okay. Yeah. So this is the field zone. Field or zones. Yeah. So this is a nice looking. Okay. The route lengths are not very thin, not very thick. You can change them as per the requirement and checking the standards, talking with uh, the fabricator of the PCB. Okay. Yes. So this is all about PCBs. I mean, a gist of PCB how it can be done using eSim. Yeah. By the way, generating the Gerber file is the most important step. So export, sorry, fabrication output, Gerbers. Okay, so you can run a DRC, run DRC. Okay, no agent found. Edges found. You can add the edges, but I'm not adding them currently. This is one of the errors. Otherwise, one unconnected. So this is the unconnected thing that I've left as some work. Okay, and output directory. So it will be the same directory as this. Okay. Yes, and plot also you need to add. Generate the drill files, generate map file, generate drill file, generate report file. Okay, yep. So all the files are generated. Uh, yeah. Okay. Now let me check the files. Once users workspace. Oh no, it was in foresee eSIM examples, BJT amplifier. Yeah. Not BJT. It was LM's voltage regulator. Where was it? Yeah. Yeah. So all the drill files and everything is generated. You can just open it up or some other gov view basically. Not exactly KiCad. KiCad doesn't have it. You can use gov view to view these files. Yeah. I mean, drill files are also there. One can definitely check it out. Okay. Yeah. Yeah. Now I was talking about LT Spice. So let me show you the libraries, already converted libraries available on our GitHub. So let me open up the website. Resources. DSpace KiCad converter libraries. So you can find it over here. All the parsers are available. In case you want it separately as well, you can download it. And it needs it's there in Python basically. So you can try it out. Okay. And LT-Space converter also similarly it's done in Python. So here the steps are given. You can try them out. Examples are given. There are around 1,000 converted files which you can find over here. Okay, converted libraries. So yeah, 1,000 examples available in LT Spice. You can just download them from here. Okay. Yeah. So is my screen not visible?
It's visible.
Yeah. Okay. Okay. So any doubts? Anything else you want to know? Hello. Hello. Yeah. Pradha MRK. Do you have any query? I see you raising your hand. No, any queries as such up till now? I mean, I'm almost done. So if you want to know something specifically, yeah, any queries? Any queries as such? Any queries? Or shall we go for the lunch? Any message? Any queries? Okay, then. Thank you for joining. We will go for the lunch and we'll continue at 2 p.m. exactly. Okay. Thank you all for joining. Attendance form is available over here. Yeah. Okay. Thank you. Thank you. Thank you all. Let's go for the lunch. Deepak, you can ask them to join at 2 p.m. Hello, Deepak, are you there?
Manta, I will share the screen that.
Uh-huh. Recording is available on YouTube. We are streaming it live. Just let me share the links. Shanti has already shared. I am sharing it again. Shanti, can you share it again? Otherwise, yeah, I am sharing it again. Ah, Shanti has shared. Yes. Pin it. Yeah. So recordings you can join here. Yeah. If anything, just feel free to contact us. Thank you. Participate on hackathon. So I will share the link. This is the link to the Scilab hackathon. So you can go there and participate. Register and participate, basically. Yeah. Okay. Thank you, Kartikeyan. Thank you for being engaged over the 3 4 days. Sorry, 4 days. Sir, will it be possible after the end of the just I am asking for what will be available, Avinash? The live streaming, yeah. Live streaming will be available throughout the sessions. I mean, it will be available indefinitely on our Fossey YouTube channel. Yeah, it will be available, Avinash. Anything else? Okay, thank you. Thank you all. Okay, bye then. See you at 2 p.m. So at 2 p.m. we have one wonderful session by Vladek Levinsky. So we'll do it. Okay. Hi, Vladek. Hi, Vladek. Hello.
I'm connected. Good morning from Europe. It's good afternoon to
Yeah.
all.
Good morning, Vladek. So
Good
we
morning.
yeah. So now we had the lunch time.
Right.
So we start after 10 minutes.
Yeah. Take your time. I'm ready as soon
Okay. So
you
I will
you will
introduce you
open
to the
the
topic.
afternoon session.
Yeah. Okay. और 5 मिनट ऐसे Yeah, Ladek, can you stop sharing so that I can share?
Yes, sure.
I guess let's start. Is the time? Okay, let's wait for 1 or 2 minutes and then we'll start. Okay, so let's start. Yeah, so welcome to the afternoon session of day 4. So this is the final session for the faculty development program on VLSI design using eSim and Open PDKs. Okay, and today we have Mr. Ladek, Dr. Vladek Grevinsky. So he will be talking about Open PDKs and also IHP PDK. Okay, and its integration with eSIM, a bit of it. So Vladek has a lot of things in his profile, and he has a lot of experience. He has worked in EPFL, then Motorola, then he was also with ETS Zurich, Switzerland. He's also involved with various IEEE sections and coordinating globally to have this open source ecosystem. Okay, and he is also coordinating with the IHP team. He regularly attends the mixed test conferences. Recently, the mixed test conference in Europe. Okay, so he has authored more than 70 papers. Yeah, and yeah, so welcome, Vladek, and over to you. Hope this will be an enriching session.
Good morning from Europe. Good afternoon. I appreciate invitation to your workshop. Program is full with really huge variety topics of related to open source IC design and Open PDK. I would like to focus on Open PDK and open source tools. I guess majority you already know, but I will give you a couple of examples, all what is now available in Open PDK. I will stop my video, share the screen, and reconnect. Just a second. I will stop sharing video, open my screen. I guess you can see my slide changing.
It's visible.
Very well. So again, good
Are you changing the
afternoon.
slides? Are you changing the slides? Just change it once.
Again,
Yeah.
so this is title page and
Yeah.
then outline.
No, next slide is not changing. Slides are not changing. It's
This and now can you see slide changing?
no. Can you share again?
I'm stopping sharing.
Yeah. Earlier, when you were sharing, it was working. Let's try it again.
Okay, now I'm making. No, it's wrong slide. Sorry for this mess. I selected.
No worries.
Yes, sure. And is it full screen now?
Yes, full screen, but not changing.
And
Now it's changing. Yeah.
okay, sorry for this, for the mess. Each time I'm selecting wrong window. Okay, we are set. So again, I really appreciate your invitation. It's a great event. I've seen full agenda, and we are interacting with Sumanto for quite some time. I'm following all the development within the FOSSI project, in particular within eSim sub-project. And my interactions goes back to very first contacts with Professor Muta Galaya. And I hope he is still active and support all the work and promotion of open source tools, in particular eSim project across the India, and surely it will have international impact. I will go.
Yes, just to interrupt. Sorry to interrupt you. Yeah, he did attend in the first day, Professor Kanan.
Okay, great. I miss first day.
Yeah,
So today I will go through this couple of points. Start with motivation. And this is critical point to bring a younger generation to microelectronics, and we see this depleted growing talent gap in microelectronics in Europe. This may be already the case in India. All even before Open PDK initiative started very dynamically with FOSSI project, in particular eSim promotion of open source tools. I will show you what is available elsewhere with new PDKs coming in. Then I will give short introduction to IHP Open PDK and the FOSS free open source software for IC design, which we maintain. So this will be going from technology, devices, and application. And then we want to continue. So our main question is what is next and how to facilitate further developments. And as usual, there will be a couple of unknowns at the very end. So motivation, building talent, this is a critical point, in particular in Europe. I did not really see the statistics in India, but microelectronics in India is developing very fast. So we have to make sure that younger generation of student designers, researchers in microelectronics will join our activities, all microelectronics domain. This has been a rise already almost 3 years ago, and now recent statistics are really scaring. We are missing across the Europe a huge number of technician engineers, and other points. Europe is aging, and you see about 30% of technicians and engineers, designers will retire within the next 4 to 6 years. So we have to make sure that, and we still strongly believe that Open PDK, open source tools, is great teaching education platform, bringing younger generation to microelectronics. Later you can read all the comments which are scaring, but we have solution. Open PDK is a solution for this. All started with eSim program even before Open PDK. I'm using this slide. You're very familiar with this initiative, but I'm using this slide elsewhere, making presentation across the Europe and internationally. All what you did, it's outstanding open source environment to bring younger generation, even student from maybe not primary, but secondary school, colleges, and introduce them to microelectronic, PCB design, chip design, and I'm really glad seeing you put so much attention to enable access to Open PDKs, in particular IHP Open PDK, which is fully integrated with your platform. This is a great achievement and surely will be beneficial to all with whom currently working. Open PDK, it was a project started by Google. They were calling this Open Silicon, and they managed to convince two foundries, Skywater and Global Foundry in United States, to Open PDK, lower administrative costs, removing barriers with paperwork, NDA, all this legal procedure to access PDK. Then Fabless, now Chip Foundry and Wafer Space, they are maintaining tape outs, giving access to both technologies. A student can design and manufacture chips. They also maintaining design platform, complete tool chain for analog, RF, and digital circuit synthesis. Immediately, this draw a lot of attention in China. They have project or program they call One Student, One Chip. And this is great initiative. If you look at the statistics, they are claiming about 10,000 students involved in the initiative doing a design. Okay, this number could be rather low for China, but I would be more than happy seeing such huge numbers across the Europe and elsewhere. I guess you may have even more students following Open PDK and using open source tools for circuit design. They are doing this not on the software level, but they have very first foundry IC Sport offering quite advanced CMOS platform at level of 55 nanometers. So this is great. All other currently available PDKs are not at such level of integration. In China, in Japan, they have other initiatives. They follow the concept of Google and working with Chip Foundry and Wafer Space to enable access to local foundries. At the moment, access it's only for Japanese students and researchers, but it's developing very fast. So I'm expecting they will open minimal fab and Tokai Rika also to international project. And as you see, this community is growing fast. Also top level government institutions are involved and supporting this in Japan. I know a little bit less about your region, but it's great to see, for example, a lot of movements across the border in Bangladesh. They call this initiative Silicon River. Further down, Asia Pacific, like Malaysia, Philippines, Vietnam, it's catching up very fast. So all this movement in open source domain is getting truly international scale. Brazil is coming up. This page is in Portuguese, so Brazilian. I cannot read, but it's very important to have also website access points in local language, enabling students who are just learning not only microelectronics, but English, and having something in their own local language is very important. I was surprised seeing FOSI spoken tutorials also translate to Portuguese. And you locally in India, you have a huge community of Portuguese speakers, and surely our partners, students, researchers in Brazil, they can benefit accessing spoken tutorials developed by FOSI Foundation in India. We are promoting at IHP Open PDK since 4 years, and this page summarized all major technical specification of our project, our process. Currently, Open PDKs cover the technology which internally we call SG13G2. It's based on standard CMOS platform with all components, including Schottky antenna diodes, ESD protections, all MOS transistor, dedicated NMOS varactors. There are also passive components, resistors and capacitors available, and backend all metallization goes up to 7 layers of aluminum. Soon we will have also copper option, which is quite critical, important for RF design. At the top of CMOS platform, we built a layer of silicon germanium bipolar devices, HBTs, and these devices are operating up to 450 gigahertz, so half a tera at silicon germanium devices. This is a unique top-level performance available offered by IHP. This process is high performance. It's only one in Europe, and with this performance, I guess it's also only one internationally. We are moving further, and very soon we will have a new enhanced version, G3CU with copper, and devices are targeted to operate up to 650 gigahertz. This is high-end gigahertz frequency range, again, not available for other BiCMOS processes internationally. And this option, G3CU, will have up to 4 layers of copper, thick copper at the back end. CMOS interconnections are 2 layers of CMOS. Bottom line are references with all GitHub internet links to documentation how to access OpenPDK install. We also provide dedicated online courses where you can learn not only about technology itself, but complete analog RF design flow and digital synthesis. Just follow the links at the bottom of this page. PDK is any PDK. It's a huge database where you have full information about available devices. It could be passive, active, basic digital blocks. Each of the devices, like inductor, they have their own numerical representation. All active devices, in this case MOSFET, bipolars, they have their own representation in SPICE library, which are available in OpenPDK. basic digital building blocks. So they have symbolic representation and Verilog instance for complete circuit synthesis. Then each element has also layout representation in PDK, and we are using industry standard GDS2 layout format to describe passive components like here, spiral inductor, MOSFET device, or basic inverter built using P and NMOS transistors. Most left-hand side, the backhand information and also process intake and TCAT specification. These are not really part of PDK, but gives a lot of initial information for all who are working on new devices, improving passive components. So we provide this information as well. Again, TCAT and using free open source software for numerical process and device simulation. It's not a part of standard PDK, but this information also are available and students, young researchers, they can learn more about semiconductor devices performing numerical simulation. I guess majority of you are familiar with ngSpice for circuit level simulation, but it has a CIDR option. This is a numerical simulator where you can analyze performance of semiconductor devices running basic 2D numerical simulation. For advanced application, have a look at such simulators like eSim or Congenda. Both are offering advanced simulation at 2D or 3D level. And there are plenty of others. Among them, it's Sharon. This is a device simulator, numerical 2D simulator, which can simulate in this particular example shown on right-hand side, single radiation effects in the MOSFETs. So you can run radiation hardness, analyze memory response to such effects in the device. Open PDK, it's huge database, which you have to install locally to start the design. Has information needed to start digital circuit synthesis. And this process, digital circuit design or digital circuit synthesis, it's fully automated. So we started using OpenRoad, a huge set of tools to create your very first digital circuit, digital chip. You are starting with a high-level behavioral description of your circuit or digital block, usually in Verilog or RTL or VHDL, and then tools assist you through all steps needed to do logic synthesis, floor planning, placement. You have all options to verify and optimize the clock, then complete routing, going down to GDS layout, clean, ready to submit for manufacturing. At each stage, there are a couple of additional tools you can access, like Yosys, OpenRoad, or K-layout for your chip routing, placement, inspection, as you can see on the window on the left-hand side. Bottom of the slides, again, there are links to OpenRoad, and now we are moving to LibreLine, which is other tool available for digital synthesis. In Europe, we have a couple of other alternatives. LP6 laboratory at Sorbonne University, they are developing this huge set of different tools for digital design and synthesis. Just follow the link to see what is available or provided by the LIP6 lab in Paris. I mentioned that we are moving to new locally maintained LibreLine in Europe, offering a complete digital design flow. So we move from OpenLine to LibreLine. And again, bottom line gives you all the links. It's fully integrated flow with a really great interface to supporting tools, and following this couple of steps in the digital design, you are coming from top level behavioral description, RTL, Verilog, VHDL, down to tape out ready layout. Again, bottom line gives you all the references. There are, of course, a couple of simpler tools which are beneficial for to introduce the younger generation of students. You can start with basic digital schematic entry, analyze simple blocks, going step by step, helping a student to understand digital synthesis. By CMOS process and IHP PDK has plenty of options, technology options, which are important for analog RF design. And IHP team built a complete open source design flow to support your RF design. It's not fully automated as digital synthesis. You have access to all the tools which should be locally installed, and then you can start with schematic entry, creating schematics of your analog RF circuit or building block. We are supporting quarks at XChem, and in the background of schematic editors, we are supporting SPICE level simulators like ngSpice and ZEISS. As soon as you complete the schematic entry around circuit level simulation, you are moving to layout drawing, create a layout representation of your circuit. And we recommend K-Layout and Magic. Both tools, they have all options to verify and validate your layout, including DRC, design rule check, and LVS. You are comparing layout versus your aerial schematic entry. If both are okay, you can do to next level. We provide industry grade quality parasitic extraction. These are quite critical in particular for analog RF design. Parasitic extraction generates all physical verification and post layout description of your circuit, which you can simulate with ngSpice and ZEISS, comparing with your initial simulation to make sure that your analog device or analog circuit works properly. Then we go through final steps down to sign off GDS2 generation for tape out, and IHP is handling chip manufacturing. We are supporting individual tools installation, helping to set up this complete flow from schematic layout, parasitic extraction to sign off and tape out. But then you can have a look at alternatives. Professor Pretel and his team at Linz University, they are supporting Dockers, images of all components, which I briefly introduced just above. You can access this kind of database of Dockers, and they are well maintained and regularly are updated. There are also other resources where you can see and eventually access all other tools for circuit design. And example is the for CDA tools wiki, also well maintained online. If you are analog designer, and in particular high frequency gigahertz range frequency chip designer, you can also benefit on EM simulation, in particular for passive components, RF passive components like transmission lines, spiral inductors, or integrated antenna. And within RF open source design flow, we are supporting numerical simulators like OpenEMS, Elmer, and Palace. Our industrial partners making attempt to automatize this flow. It's initial stage, but highly motivating. It's impressive work by our partners at Infineon in Villach in Austria. They are putting all the models which I explained or introduced in earlier slides, creating a framework to do full automatization. At the moment, as you see, all is based on proprietary PDK and commercial tools, but these purple blocks are introducing step by step. So the team is switching from commercial tools to open source, or allowing you kind of smooth interaction on each stage between commercial EDA tools and open source tools. The MAGIC framework, IC design framework, was introduced already 2 years ago at one of the Mosaic workshop at DESDET conference. So you can see the complete presentation online. And again, Leipzig's lab at Sorbonne University are offering or working on alternative implementation of fully automated flow. It's a little bit simpler than Mosaic, but you have all important automatization steps, starting with analog design, sizing of the chips. There is a lot of Python tools helping you optimize netlist or reviewing performance of analog blocks, going to layout generation, of course, including parameter extraction. If you manage to close this loop, you are ready to submit your chip for manufacturing. The tool is maintained by Jean-Paul Chaput at Sorbonne University. There is his contact. If you are analog designers, you're more than welcome to try the tool. If you are software developers, you eventually can assist Jean-Paul with further developments. Quarks has been already mentioned a few times. It's fully integrated with IHP Open PDK. The front end is really well developed. It includes not only schematic entry, but all post-processing of results with all critical options to analyze RF simulation data. We are supporting not only tools which are developed in Europe, like eSim for schematic entry. The schematic eSim, it's well integrated with Magic tool, which is alternative to K layout for editing, reviewing layout, GDS representation of your layout. And this tool is well integrated with Skywater and global Foundry PDKs, Open PDKs maintained in the USA. K-Layout is our main tool. It's open source tool developed and maintained locally in Europe. Alternatives like Revolution ETAs are coming very quickly. We are at initial evaluation of other tools at IHP as well. You design your analog RF digital block, but to test the device, you need a PCB as a test bench to place your circuit chip and connect with test instrumentation. To design PCB, we recommend KiCad. It's open source, industry-grade quality tool, has a simple schematic entry. It's not just schematic entry, but KiCad support transistor level, circuit level simulation with ngSpice, and for some digital block, ngSpice drives mixed mode simulation with xSpice. All this has been introduced, and integration has been well presented and documented online. Just follow the links at the bottom of the page. I mentioned importance of electromagnetic simulation, in particular for all who are designing analog RF chip, in particular RF chip, high frequency, high-end gigahertz frequency range. You can partition your circuit, RF subcircuit, identify passive RF components, like here. On the left-hand side, there's representation of GDS layout of a spiral inductor. Identifying inductor, you can create 3D representation for full electromagnetic microwave simulation using numerical simulator. Simulator analyzes the circuit, generates some output like S parameters or lumped element block, which you can then include to your schematic, reruns analog RF simulation with ngSpice. You have spice level output from EM simulator, and it's much faster than going through full 3D numerical simulation. Again, bottom line gives you a pointer to first introduction and other documentation of EMS, Open EMS electromagnetic simulator. Okay, this is yet another simulation example of spiral inductors. You see the performance of your selected devices. Then from this, through Python interface, you are getting S parameter blocks, lumped elements, subcircuit, which you can include into transistor level circuit simulation with ngSpice or other open source SPICE simulators. We do not support MEMS devices in our PDK, but this is already dynamically developing domain, and there are plenty of MEMS for variety of applications. Have a look also in this domain. There is a lot of research ongoing, in particular for electromechanical numerical simulation tools. I'm more on compact SPICE modeling, and to introduce new device into circuit simulation at SPICE level, we are using Verilog behavioral modeling language to describe any semiconductor devices. This could be a passive components. I already pointed to transmission line, spiral inductors, antenna. You can think about cross-domain devices like optoelectronics, of course, all active semiconductor devices, like in this case, MOSFET transistor or bipolar transistor can be described using Verilog behavioral language. This example is very simple representation of AKV MOSFET long channel device coded in Verilog. Introduction to Verilog A modeling probably would need yet another language, so I will suggest you to follow the links at the bottom of the page to see what benefits gives you Verilog standard, how to code the model, and bring it to simulators. Maybe I will skip this slide, but cryo temperature modeling is quite critical now. We're talking about quantum computing, where interfacing circuits are operating really at the level of couple of kelvins, even below what we have in this example. If you are in this domain, you will have a couple of alternatives, and I suggest to review the papers listed at this slide as well. So we can have a Verilog representation of semiconductor device, passive, active, or even digital blocks, and to bring it to simulator and enable a transistor level or subcircuit level simulation using ngSpice, we can use OpenVAF, very advanced Verilog compiler, which brings model as the dynamic library to target simulation. We are supporting ngSpice Zeiss. It's at initial integration state. Recently, noise has been added to ngSpice. This is an important feature added to support analog RF design. We have, of course, open source alternative. GNU-CAP team is working on full Verilog AMS implementation, and the work by GNU-CAP team has been presented at a couple of other open source events, including FOSDEM conference. By the way, FOSDEM is one of the largest open source conference in Europe. So if you are in this domain, have a look, and maybe you have something to contribute as well. Then having a Verilog model in Verilog, compile, bringing is through interface to ngSpice. Designer see only one extra line where you point to the dynamic library, which includes new Verilog A model. In this case, I use other one, which I briefly present, long channel, AKV long channel MOSFET model. And with this one extra command line, everything else is transparent to the user. There are no extra modification needed in the input file for transistor level simulation. In this particular case with ngSpice. This is a little bit higher level contribution to Open PDK. Open PDK, it's huge database, includes a lot of statistical information to run Monte Carlo kernel models to make sure that your design will be fully functional after fabrication. To support statistical modeling, we submitted a very dedicated mismatch evaluation chip. This is huge matrix of MOSFET devices. We can access more than 60,000 devices. It's important to have a lot of information to create statistical data. In this particular example, the chip is dedicated for short distance matching, which describes local variation between single transistor in your chip. This has been designed, it's manufactured, so we will start testing a silicon very soon. Measurements and characterization is critical part. This is kind of bottleneck. Not all research group, they have well-equipped lab. But I'm bringing this example that you can introduce your students to microelectronics chip testing with very simple smartphone application. You can have one mobile device, which is your mobile smartphone signal generator connected to, in this case, very simple RC circuit, and other smartphone, it operates as an oscilloscope, and you can build very simple basic test cases to introduce your students to microelectronics characterization or chip or characterization. There are two different set of smartphone application. They are running on Android and Apple iPhones, and bottom lines give you the references where you can download this free open source software also for your smartphone. So microelectronic testing coming to the level of your mobile device, which are using to send a WhatsApp message or whatever you prefer, but you can use this in your lab to introduce newcomers, young students to microelectronic testing. Of course, there are a couple of other open source hardware chips to do similar measurements. Here I use Espotec chip to build a simple test environment to measure CMOS inverter. This on left-hand side, this post-stamp size PCB include the chip, which has 2 channels function generator, 2 channels scope, voltmeters, and of course, control power supply. Setting up basic test circuit to analyze CMOS inverter. On your computer screen, you see the output measured by integrated two scopes. If you do not have access to hardware, of course, you can simulate. So this is a quarks representation of basic CMOS inverter, and you can see similar output measured and simulated. What would be interesting to have full integration, measurements hardware and quark simulation in one package. So this is my suggestion, to have a look at both tools and eventually think about complete integration. It would be really great to have your involvements in such a tiny project to support measurements and characterization. Others are going a little bit beyond. Professor Kinget from Columbia, he created a chip he called Mosbius, which has not single device, but huge matrix of MOSFET devices. You can see this as analog FPGA, allowing to configure not single device, but couple MOSFET devices, creating basic analog building blocks, and then connecting to some measurements equipment and having using this for your microelectronic class or laboratory. And Professor Kinnett supports this as open source design with all examples guiding you through measurements characterization for your class to understand single transistor performance or behavior of basic analog building blocks. There is a tiny alternative, much smaller, developed by Professor Knack at California, University of California. We have access to technology. We have open source PDK, completely established analog and digital design flows. And to help you to understand installation design flows, we are offering both digital design courses and analog design courses. Both are available online. You just follow the links which I'm listing here, and you can use this also for your classes. If you need any assistance, just drop me email or contact directly IHP. We can assist not only with installation, but helping you manage all the documentation and run training courses. All who are local attending IHP courses in person are also receiving design certificates. So we discuss Open PDK, open source tools, but all this leads to a hardware which has been taped out and manufactured by IHP. Of course, IHP was very first to design chips. Here we have open security hardware model, which has been created with using open processor available in open source domain, using open source EDA tools, and of course, complete Open PDK provided by IHP. It's very first design, manufactured, and bottom photo shows the chips under test. So we complete the flow from design, manufacturing to successful testing. Details about these particle chips are within the links at the bottom of the page. We are interacting with other university partners. In particular, ETH Technical University in Zurich is very active, and here you see the design which they created SoC with RISC-V processor. It's relatively tiny chips with a couple of mega gates, but it is fully functional RISC-V 64-bit processor running Linux. The chip has been manufactured, assembled, tested, and it boots Linux. So you can build your own CPU and you have fully functional Linux computer designed with Open PDK and Open EDA tools. There are more designs which were submitted last 2 years, 24 and 25. It includes also legacy processors, digital blocks, but like 6502, but also quite advanced millimeter wave chips in the tape-outs. In particular, last year, spring tape-out has been fully loaded with submission covering high-end gigahertz frequency RF chips. As you can see, chips are going up to 160 gigahertz, 180, really high-end RF. These chips has been manufactured. We are expecting designers who submitted the chips to test all RF blocks. What was surprise, at least for myself, selected chips has been submitted from the students in Bangladesh. I already mentioned Bangladesh is catching up very fast, and there are a lot of expertise is growing across the country. I'm sure this is also case. So have a look at IHP, Open PDK, and open source tools to build your design. Again, middle of next year, we have even higher frequency chips reaching 200 gigahertz, fully integrated within IHP process. Last 2 years, we were offering also free manufacturing, but budget is limited. Now we are trying to find a low-cost solution to support chip manufacturing. If you are using only CMOS design, in particular for digital design, we have simplified PDK we call CMOS S5L. It's pure CMOS with 5 metal layers, and depending on number submission, the cost per millimeter square can go down as low as 1,000 euro. It's still 1,000 euro, but much lower cost of manufacturing than offered by other multi-wafer project wafer fabs. Of course, high-end, fully featured by CMOS process, SG13G2. It's a little bit more expensive, but again, this is only one high performance by CMOS process available internationally, not in Europe only, but internationally. You cannot find by CMOS process with this performance elsewhere. To summarize, I'm following eSim, and all this work was done before Open PDK initiative. In particular, eSim team created outstanding online development platform to introduce students to microelectronics, not only for PCB design. Now they are moving to IHP Open PDK. They are supporting Skywater too. And the platform they created should be ported also elsewhere, for example, to Europe. In Europe, we do not have such teaching education platform as eSim FOSSI. I already introduced the Google initiative of Google Silicon. You already know that Japan and China is also opening selected foundry offering Open PDK. And very recently, I was happy to learn that your SCL lab, India lab, also opened very first PDK in India. This is a breakthrough, and I'm sure this will accelerate all open source design movement, in particular India. I hope the process will be open for international submission. IHP is very first, unfortunately, only one in Europe research institution offering Open PDK. I hope we will convince more European founders to join this initiative. If you are IEEE member, you probably familiar with solid state and CAS initiative. They are very active promoters of Open PDK. In particular, IEEE solid state with PICO program. Search internet for all this information from quite regularly. They are offering calls where you can submit and eventually obtain financial support for your chip manufacturing. I'm IEEE EDS, Electron Device Society member, but our EDS, it's a little bit behind. They very recently started with the new initiative. In fact, they pushed this at IEEE level. They call this Open Silicon. So I hope through Electron Devices, we can get also some financial support for open source chip design and its manufacturing. Bottom logo, it's well-known RISC-V. All who are in digital design, they're using open source RISC-V architecture to submit digital designs. What next? In Europe, there is quite dynamic development, but we need kind of to consolidate and all activities, make sure that we can interact with different groups and work jointly. Back in 2024, FOSSI Foundation, together with Go IT project, they created open source EDA roadmap for Europe. This initiative or roadmap has been recognized by European authorities, and it's led to free open calls to support all within microelectronics domain related to open source. This ended with a free project for digital, analog, and productivity, and we managed to, EU is offering about 50 million euros to support this free complementary project about to start now. Through this, I hope we will also secure some budget to support open source design and Open PDK manufacturing, at least across the Europe. As you see, it's huge consortia with, in particular in analog domain, we have 27 partners from 14 countries working to consolidate and integrate open source EDA tools to support Open PDK designs and manufacturing. There is a lot of activities going beyond Open PDK, and we are trying to convince European Union to support such initiative like a reference fab, which would be fully dedicated to open source design and Open PDK chip manufacturing. It's very ambitious, it's high-end target. I hope this will draw some attention at EU, European Commission level in Brussels. So stay tuned. I hope next time I will bring some more news. All what I was presenting, it's huge team effort. At IHP Open PDK, it's coordinated by René Scholz. He's the key person leading not only Open PDK project, but assisting all within open source tools design, and his team created this outstanding environment to support open source design for analog RF as well digital. We obtain significant financial support at initial state, mainly through German funding at local level. It's Forschungsfabrik Microelectronics. It's funding organization in Germany, in particular Brandenburg land, and as well Federal Ministry of Education and Research. We want to go further. All contributors to open source EDA roadmap for Europe managed to convince European Union, and I hope this will be a breakthrough not only in Europe but internationally in open source chip design internationally. If you are willing to learn more about open source chip design, Open PDKs, we have a couple of events. I already contributed earlier in my introducing Open PDK at Spanish Chip Chair. It's high-end Association of Microelectronic Design Universities. Before Mixes conference in Poland just last week, we ran well-attended Open PDK workshop. Upcoming is Open PDK discussion at Free Silicon Conference in Ljubljana. In the program, I've seen also submission from India, from eSim group. I hope they can present their work quite soon. For your Asia South Pacific, we are also supporting some activities in China. Then later in September, we will go for ESDER conference at Palma de Mallorca. If everything will go smoothly, there will be also Open PDK session at ICTA conference in Singapore. End of year, we will close with online workshop as usually in December. So by this, I'm closing my presentation. And if there is any questions, I be more than happy to have some interaction with all who are joining today's workshop. So closing again, Sumanta, thank you very much for your kind invitation. I'm really glad, really happy to join your event, and I hope my talk brought some updates on open source PDK, open source tools, activities, not only in Europe, but internationally.
Thank you, Vladek, for joining and speaking and giving insights of, I would say, whatever is happening globally. A lot of initiatives, a lot of things to have open source, open PDKs, and open source ED ecosystem throughout the globe. So it was wonderful hearing to you, and we are happy to collaborate with you for so many years until now. So anyone wants to ask any questions? Vladek is a very experienced person. He would be happy to answer your questions. Any questions from the audience? Vladek has given a good amount of presentation, a good amount of gist of everything. I mean, he has briefed every possible thing going on in the open source domain. Yeah, he has also shared the slides. Okay. Yeah, so any questions from the audience?
I also added my email address. If you have something
Yeah,
or you recall any questions, you would need any updates, just drop me email. I put in the chat window.
sure. Thank you, Vladek, again. Hope to see you again in another event of FOSI, eSIM team.
Yes, I'm looking forward. This would be great to meet. There are some plans to coordinate certain actions which could lead to even in-person meetings. So
Sure.
I'm looking forward to meet you and your partners quite soon. I
Yeah.
hope we'll make some arrangements.
Thank you, Vladek.
Okay, thank you very much. It was great meeting you online, and looking forward to next opportunity. Thank you very much.
Thank you. Bye. Okay, so we can perhaps have a short tea break of 10-15 minutes, and then we can continue with our hands-on. So I'll be talking about how to run a circuit using IHP PDK and eSIM. So first of all, we need to install the IHP PDK since it's not available in the eSIM 2.5 version. We will make it available in the future versions of eSIM. So yeah. So should we continue or have a tea break, everyone? Your opinion? Okay. Yep. Someone is saying continue. Tea break. Okay, continue. Okay. Okay, then let's continue. More people are asking for continuing. Okay. Okay, then let's share the screen. Let me share the screen. So yeah, I didn't talk about. Yeah, by the way, I had so due to some technical issues, I wasn't able to complete the VHDL simulation, but I have it now ready in the eSIM window in Ubuntu. So yeah, so these are the command messages like of the PWM decrement. So we are sending the signals, and yeah, and receiving the signals. Basically, GHDL is talking to the ngSpice through the socket communication, and we got the plots over here. Okay. Okay. So yeah. So this is the op amp. So if we check the schematic, So we are sending it to the comparator, and this is the data. Okay, so this is the output. So you can see the data and the output, and other pins also are there. So PWM in. So since it's digital, I will show you the stacked waveform. Yeah. So PWL in signal is just a constant 3 volts, and yeah, that's all. Yeah, RC1. Let me check the RC1. Yeah. Yeah, so you can even see the RC1 signal. Okay. So as you can see, the PWM signal is decreasing. The duty cycle of the PWM is decreasing. So this is with certain amount of um, certain percentage. This is the output. So yeah, so this is how you simulate using NGHDL. Okay, and I will just close this as well. Okay. Now I also had to show you the Sky 130 PDK available in eSim. So this is the link for the, so we provide only the Foundry primitive libraries. FD stands for Foundry, as Vipul said yesterday, and PR stands for the primitive libraries. Okay, so these are primitively available from the Foundry, and yeah, so these are the cells. So we have the cells directory, and here we have all the components and different components present over here, including capacitors. So we have HVT. People already said about HVT, LVT for low voltage threshold. So and then NIM capacitors. Okay, then no shield. Then yeah, different kinds of capacitors. You can refer to the documentation of Sky 130 PDK. So there you will find the details. We also have diodes, different kinds of diodes. So 5.5 volts, LVT, HVT. Okay. Then inductors and FETs. Again, LVT and FET, NVT and FET, 20V0, then ISO. So just check the documentation once. And Vipul yesterday has talked very well and explained all the concepts. Resistor generic, N diffusion, then P diffusion, then high poly resistor. So yeah, then RF blocks, RF and FET. Okay, so all these are the contents of the Sky 130 PDK. Okay, the cells in the Sky 130. Now going to the models. So we have capacitors, different model files. You can try running this model files. Okay, let me turn on the my video. So let me turn off the video. Yeah, going back to the details. So Sonos, then different corners. So we have FF corner, FS corner, SF corner, SS corner, and TT corner. Okay. So yesterday, whatever Shanti showed is TT corner. We can change the corners even in eSIM just by typing the label. Okay. And yeah, so the tech files. So we have this TLF file over here. Okay. Yeah, so in the model file, this sky130.lib.spice file is the most important file, which needs to be imported while running. I mean, it contains everything. So it includes all the other cells and other model files. Okay. So you need to import this file in order to run something using Sky 130. We haven't included the standard cells since we are not doing doing the synthesis in this step. We are only into simulation, but yeah, so we may include it in the future as a future scope. But yeah, as of now, we have the Sky 130 primitive libraries. So, any queries up till now regarding Sky 130? Any queries? Okay, no queries. Then going back. Then yeah, so we will be now installing the IHP PDK. So just copy this link in the. I'm pasting this link in the chat box. Okay, and please download all the files. Example.cir, then IHP install script.sh and install ngspice latest.sh. These are the important files. Please download them. I'm waiting for some time. Okay, have you downloaded the files? Yes, no, something, thumbs up, thumbs down. Just reply something in the chat box. Please download all the files present in the folder. There are 4 files. Spice Init is not very necessary, but rest 3 of them you need to download. Okay. Yes, no, just give some thumbs up or something to let me know that you have downloaded them. Okay, nice, nice. Okay, just to make you aware, so we will be installing ngSpice 46 plus for this IHP simulation. Otherwise, and while eSim 2.5 works on ngSpice 35. So once your work is done, just you need to port back to ngSpice 35. I will show you how. Okay. So yeah, now creating a new this thing and then yeah. So I have already downloaded all the files over here. Okay. So let me change the permissions of the files. So chmod 777 IHP, just press the tab key. IHP install -install script.sh. Okay.
Sumanta, can you zoom in a little bit?
Yeah. I
Yeah,
hope this is visible.
it's fine.
777. Yeah, by the way, this can be done in Linux based environment. In the future versions of eSim, we will have it on Windows as well. Okay. Okay, so I made changes to the permissions of these files. Now I will run the install script for ngSpice first. So just run /install, enter. It will take some time to load it and install it. Yeah, so it may ask for the password. Okay, so until then, how many of you are following me and doing it side by side? Just give a thumbs up or not. Vivek, so yeah, no, so it will work in Windows only. Sorry, Linux only, or subsystem of Linux or something. A Linux-based environment is required. So to repeat the process, I just downloaded these files. I've already sent the link in the chat. Okay. So download these files and run it on your system. Just change the permissions using chmod 777 and run it on your system. And install the ngSpice and the ISP PDKs will be installed. So currently it's installing the latest version of ngSpice. How many of you are able to follow? Just give a thumbs up, or at which step are you in? You download the files? Okay, nice. Okay, so ngSpice has been installed. Let's type ngSpice -version. So we see ngSpice 46 plus has been installed on our system. Okay. Now I will just install the IHP PDK. Install. So yeah, so just run this command dot backslash dot slash IHP hyphen install script dot sh double hyphen install and IHP Open PDK installation for eSim. So check if ngSpice has OSDI support. So OSDI and OpenWAF will be required. Verilog A support of ngSpice will be required over here, which Vladek just now talked about. So it will be so we have already compiled it through the script using enable OSDI command. Now for installing IHP PDK, we just type yes, and it will run. It will automatically. It should be able to automatically install everything. Okay, so it's cloning the process design kit from the GitHub repository. Any query up till now? Anyone? Hello. I can see 151 people. Any response? What happened, Saranya? Any doubt? You can just type in the chat box. Saranya, Harsha. No doubts? Okay, fine. So it's recursively pulling other IHP Open PDK tech files and all. And now it's installing OpenWAF, which Vladek talked about recently. Okay, so we are done with the installation. So let me wait. Okay, Avinash. You need to click on the above link, download all these files, and save it locally on your desktop. Okay, you need to click on the following link and download the example.cir IHP hyphen install hyphen script.sh, install hyphen ngspice hyphen latest.sh files, and save it in locally on your system. Then run the following commands: chmod 777 and the script name, then chmod 777 install hyphen ngspice hyphen latest.sh file, then run the dot slash install hyphen ngspice hyphen latest.sh. This will install the ngspice latest version for ngspice 46. Please note that ngspice currently in your eSIM ngspice 35 has been installed, but we need ngspice 46. So for this we are running the following command. Okay, it contains all the scripts for installing ngspice 46 plus, and once ngspice 46 plus is installed, just run the following just check the version of ngspice. So you will get the following prompt as ngspice 46 is present already. And yeah, after running this, you need to run the following install script: ihp-install-script.sh --install command, and it will install the IHP PDK and the related dependency like OSDI and Verilog A. Okay. Avinash, is it clear? Hello, Avinash. Other people, are you trying it out, or like those who are on Linux? Okay. Thanks, Avinash. Other people are trying it out, right? Okay, Saranya. Any other comments? Anyone? Just give a thumbs up at least to, in case you are not even trying but getting what I'm trying to say. Okay, nice. Ganesh. Okay. Gufran. Okay. Okay. So once we have installed it, just run the command as dot slash sorry, just check the following script. So in case you have gedit, or let's check with vi example. So yeah, so what's there in the example script. So let me brief. It's just a netlist file to check the installation of this ISP PDK. So the first line is this one, dot cir. This is a comment. Okay, just the headline. Then we are giving the title to the netlist: nmos dc test using HP SG132 TT corner. So we are trying to simulate in the TT corner. Okay, then we have the lib file. So we are adding the library file. So this is the correct link which you need to add. So in my case, it will be installed in the home directory. So I will just go to my home directory and show you what's there inside. So this is the HP PDK installed inside the home directory, and this is the OpenWF. Okay, so a binary file, and this is the SP PDK, same as Sky 130 PDK. And here other files are there, make file and all for installation. And yeah, so rest all files are there, doc and all, which you can explore later on. Doc contains all the documents and layout rules and so on, simulation rules and so on. References, yeah, so primitive libraries, GDS and all it contains. Okay, and QA, standard cells. Okay, then DRC, everything related to DRCs and all. Okay, now libs.tech file. So here we have the files for required, the tech files for required for all the software. So those who want to work with Magic also has Magic files for Magic, and then GDS Factory, K layout, LibreLane, and so on. So our matter of concern is ngSpice. So so we have the OSDI. Just check it. OSDI. These 4 files should be present. Okay. And models, capacitors are there. Then mismatch different capacitors, and MOS high voltage corner, MOS low voltage corner. Okay, then corner resistor, diodes, resistors. Okay, bond pad, Schottky, EHD, HBT. Okay, then yeah, so all the different files are present over here. Let's open, suppose corner. Sorry, let's open it using a editor. Open with file editor, gedit. Yeah. So this is the gedit file containing this is for PSP model 103.6, and you can see the date it was generated in 2020. Okay, and different parameters and different all stuff. So we have SS corner, MOS SS corner, FF corner, and FF mismatch, SF, FS, FS, and so on and so on. Yeah. Okay, and similarly other capacitors and all are also there. So accordingly you need to include the model files. You need to refer to the documentation given over here. This is for, so all the simulations and all are present over here. Okay, and yeah, so as parameters also one can try for EM simulation. So basically it can be used for RF analog design. So one can use this PDK. Okay, layout rules are also given over here. Then process specifications and all. Okay, so yeah. So all the threshold voltages and so on are present in this doc file. Okay. So one needs to follow the guidelines given over here, and add the bit length and all the parameters, finger numbers and all in the while simulating the SPICE netlist. Okay. So yeah. So back to the SPICE file. Yeah, so .lib I have added. So since it's home Sumanto for me, so it should be home Sumanto. Other things should remain the same. For example, here we have, so this can also be done with some addition. So for example, Kirthana is there. So just it can also be done in Windows, but it's advisable to be done to do it in Ubuntu system, okay, or some Linux system, because of a lot of things which people and Ladek even suggested earlier. Then we are adding the global ground reference over here. Then bias sources as VGS net1 ground 0.4. Okay, so VGS voltage as 0.4 and VDS 0.1. Drain voltage as 0 volts, and temperature parameter is 27 temperature. And yeah, so X stands for subcircuit, M stands for MOSFET. So it's general SPICE MOS files are behaving like are taken as with the designator M1 M. So we need to name them as M1, M2, M3, but those in the PDK are in the form of SPICE netlists. So we need to use XM1, XM2, and so on. Okay, so net2, so drain gauge source substrate. Okay, so net2, then net1, then source substrate ground. Okay, then low voltage NMOS SG13, width 1.0 u and length 0.13 u and ng equal to 1 and m equal to 1. Okay. After adding all the parameters, just do dot control operating point. OP stands for operating point, saving all. One can do save all. We have commented it. And yeah, so let id drain current be equal to 11. Just to test it out, we are doing it. But in general, I'm printing the net 1 values. Again, can print just yeah. Net 2. Okay. Okay, now I'm saving this file. Okay, now let me run this file using ngSpice. Yeah, by the way, so after installing this IHP PDK, this edits your environment variables in the .bash rc file. So just try, to have a new environment loaded, just open up a new window and switch to the same location, music IHP, and just try ngSpice example.cir. Okay, so yeah, it's running currently. So we see the net 1 value is 0.4 volts and net 2 value is 1 volt. Okay. Okay, now yeah, so just this was just to test it out whether everything is loading correctly and all. So any doubts up till now? Any doubts, any query up till now? Any doubts, any query? Okay. Yeah. Anyone? Someone just unmuted, I guess. Okay, then let me go back to the slides. Sorry, to the presentation. Okay, now I will just create a inverter using eSim and try it running, and I will edit it to match with the HP specifications, and I will show you how to do it. Okay, so inverter, just let me do it. Its project name is inverter CMOS. So whatever I am showing for the HP, this can be done for any other inverter as well, where you can use eSIM for the front end schematic development, and with slight modifications, you can, since it's an open source code, so you can even update the backend. Update the Python script and add the PDK files to the eSIM. Okay. So yeah, so let me first design a small inverter. Shanti already has shown you a Sky 130 inverter, so it will be something similar to that. So MOS N. Okay. Then MOS underscore P. Okay, I'm placing it over here. Then yeah, so we need to mirror it. So this is the button to mirror vertically. Now I place the pulse. Then ground. Yeah, I'm connecting the pulse. Now I will add VDD. Sorry, VDD stands for DC source, and I will add it over here. GND. Okay, now connecting this VDD. And then GND and connecting the wires. Okay, so the circuit is complete. Now adding the global label out, input in, and saving the netlist. Control plus S. Okay. So this is the steps. These are the steps which Shanti had shown yesterday. So any doubts, any queries related to this? Okay. Okay, now after saving this, so since I'm in Ubuntu, I'm not generating the netlist. So I just click on convert to ngSpice, give the start time 0.1 milliseconds and 10 milliseconds. Okay, and source details as 0, 5, delay time is 0.1 nanoseconds, and rise time is 0.1 nanoseconds. Fall time also is 0.1 nanoseconds. Pulse width 1 milliseconds, and time period is 2 milliseconds. Okay. Now, now let's give the voltage as 1.8 volts. Okay. And yeah, so for now I am giving the default ones, but afterwards we will change it. So this is the value for PMOS. Sorry, this was NMOS. Um, NMOS and PMOS. Okay. Now click on convert. Converted successfully. Just refreshing. So we see all the files over here. .cir, .keycad underscore sch, .proj, then .lib file, analysis file, XML file. XML contains the previous value of the simulation, and .cir.out file and most lib file. Okay, just to check it how it looks like by simulating this. Just we'll simulate. Okay, just check the input, output. Okay, so input and output. Output is too low. Okay, I mean, yeah. So we did mistake. So here also it should be 1.8 volts. Okay, convert. Okay. In this space plots, yes. Yeah, so you can see the input output using the, this is using the models already available in eSim. These are just idle models suited to 180 nanometer. Okay, and but these are not the PDK specification models. Okay, now we will switch to the now we will convert this file into PDK. So just referring to the PDK specifications in the uh, yeah, just opening up the example.cr file. Sorry, let's quit ngSpice over here. ngSpice example. Yeah, just yeah. So let me copy this, the following line. Title is not necessary. So adding it over here. and ground is obviously there, not needed, but and yeah, so we will change this NMOS. I am doing it in the eSim editor itself, but you can try it on some other editor as well. Sorry. Copy and paste it again, paste it again. We will, since it's 130 nanometer, we will do it for a lower WL values. Okay. By the way, ngSpice is kind of doesn't look for is case insensitive. So whatever case you give, it doesn't matter. But you need to take care of the naming conventions. Okay, and let's see anything else. We'll also give OP. Yeah, I was saying yesterday OP is after control the OP should be present. So after the control statement, we need to add OP. Set fit is not needed. Yeah. Yeah, I guess we are good to go. Save and exit. Going back and running it. Do you want NG spice plots? So, oh, there's an error. What is this? Very important step that I forgot. So, designator should be X instead of M1 and M2. So, saving it again and running it. Okay. There's some more errors. Yeah, so 1 micrometer is not there in the specifications. Let's check what was there in the example. So one needs to take care like what values of WLL should be given. So some random values doesn't work. So one needs to refer to the specifications given. So WL 0.13. And maybe so width of PMOS should be 2.5 times that of NMOS. So maybe I can write 0.5 over here and 0.13. Okay. Now let's go back. Is it edited properly? Yes. Now let's check if it works. Still, it's giving some errors. So let me check. We need to compare it with the original one once again, and yeah. Save all, okay, and let me check once again. Yeah, so number of fingers is 1 and multiplication number is 1. Yeah, everything looks fine. So let's check what's the issue. MS is also equal to 1. Let's change it to 1 more. Okay, now yeah, let's see what's happening. X1 out. And 4 and 1 Q. Let's also have ng equal to 1 and ng 1. 7 exit. Oh yeah, so eSIM was started without loading the PDK root. Because of that, it was not working. Me, let's try it out from a terminal. So take it once. So it's there in the eSIM workspace. And opening a terminal here in this spice. I mean, yeah, now it has got it worked. Plot v of in, plot v of out. Okay, so you can see the plot. It's the inverter plot working properly. Okay, so you can so here the PDK root was not added since we are running it from since it runs as a different project. So we had done it separately, and it's working. It works from a separate terminal. So okay, so eSIM can be used for creating this schematic and then run from a terminal. So PVT analysis can be done. Wait, let me find out some information for this. Just a moment, I will show you the PVT analysis. Yeah, so I'm sharing my screen once again. Wait, hold on. Just 1 minute. Yeah, so I found out something, but PVT, Gufran. So, what all things do you want to include in PVT? Are you there, Gufran?
Sumanta, have you shared any screen?
No, no, I'm not sharing anything. Um, I'm not sharing my screen. Yeah, Gufran. Yes, so let me share my screen. So there were a lot many queries related to Monte Carlo simulation and PVT. So for the Monte Carlo simulation, one may refer to the following documentation over ngSpice. This is the ngSpice link which I had shared earlier. Just 1 minute. Yeah, and yeah, so you can refer to this and add and try it out yourself sometime. So yes, so it's possible using ngSpice, obviously. Okay, so different parameters, UNIF and a a a UNIF, AGOS, and so on. But Gufran, so about PVT, I would like to know like what all things you are expecting in PVT. Hello. Okay. Anyways, so yeah, so I have shown you the simulation. So and since Gufran was asking, I was just exploring with since PVT stands for process temperature and voltage, so one can create a for each block and run a DC sweep for temperature variation by varying temperature and VD for various values and get the output. So I will show the graphs. Waited. Yeah. So for different temperature values, different graphs one can see, and yeah, one can definitely try out PVT's simulation and other things using this. Okay, and yeah, and I will just give a gist of the IHP PDK documentation. So So yeah, this is all about the documentation in the HPPDK and different libraries present over here. Okay, so let me open up the GitHub link of IHP so that side by side we can compare. As I said, there are different tech files present. Um, Including ngSpice models. Sorry. My screen is visible, right, Deepak?
Yes, Sumanta.
Yeah. Yeah, I mean SG13 G2 underscore IO for IO pads, then primitives, SLAN, and standard cells. Okay, so you can check them here. Digital ones are here, and yeah, and then technology libraries. So one can even create new libraries over here. So available cells, output strength, and so on. In installation, we already followed the installation script over from this from the following script. We had done this following installation script. So you can see that we are installing OpenWF and Open PDK as the IHP dependencies and Verilog models. Okay, and yeah, and yeah, I mean, this is the PDK interface module infographic and different process specifications as I have shown you in the previous documentation. In the layout rules, going to the analog design. So in this spice installation, as we have seen, the following simulation. So these are some test cases. So one is to compile with enable OHDI. So everything is added in the script, which we already had run. Okay, and yeah. Yeah, I mean, so this is the example which we had tried just now. Okay, and so I had mentioned the current already. Let's change the current and see what's the updated output. Well, let's see. Yeah. Saving it, and then let's copy the schematic here. Yep. Yeah, so the current is 1.14 microamperes, as you can see. So the current through the follow ignite we are trying to get using IDS. Okay, so yeah, it's matching the values. Similarly, yeah, other things also can be tried out using the HP PDK. So yeah, in the next versions of eSim, we will be integrating this with HP PDK. Yeah, so so it's some work is also going on with Open Road and the IHP PDK LibreLane setup. So you can go here and try it out. We are also integrating LibreLane with eSim. Soon it will be there in place. Yeah, and EM simulations can also be done. You can just one can just check it out over here. Okay. Using Open EMS and tools like that. Okay, so that's all from my side. Any doubts, any queries? Share PDK documents. Yeah, PDK documents is present over here. Do you also want to check the Sky 130 PDK documentation? So, yeah. This is the Skywater PDK documentation. Yeah. So I will also just brief. We have some time, so I will brief with the Skywater. Any doubts related to IHP? Any queries related to IHP documentation and IHP simulation? So schematic through eSim and then adding the simulation parameters and then doing the simulation from ngSpice. Any queries? Any queries, everyone? Okay, no queries then. Let me continue. Yes, so this is the Sky 130 documentation and yes, so we did work with the primitive libraries yesterday. So one can try out primitives. All the documents are given over here. You can see FD stands for Scrap Foundry, then eFabless EF and Oklahoma State University OSU and different things. Someone was asking whether it can be included with Cadence. So yes, obviously, but we highly recommend you to do it with eSim or yeah, use eSim in that too in Linux environment because it's easier. Okay, so it can be supported on different tools as you can see. So let me check register. So, yeah, so the device details are present over here. We'll share this link also in the chat. So you can go here and check the device details. Low voltage NMOS FET, then PMOS FET, and so on. Okay, so different values, the TT for TT corner, FF corner, SS corner, and so on. Minimum, nominal, and maximum values. Okay, then high voltage values are also there for PMOS, and everything is available over here. Okay. By the way, so from the eSIM team, we are also developing a lot of things. If you go to the resources page, you will see IPs. Sky 130 analog IPs. So these are the contributions from the eSIM marathon which were converted into IPs. So you can try them out in the meantime. So you need to download it. These are sub-circuit files. Varad has already shown you how to import the sub-circuit library files. So you can import them in eSim and then try simulations. Import them in eSim, create symbol. The symbols are also available over here. So upload the symbol and the sub-circuit library and then run them in eSim. Okay, similarly, we have digital libraries as well, a huge repository, we can say, and we are adding it up. Okay, so I will just share the links again over here. Yeah, so these are the things that you can see and try them yourselves. And someone was asking about the number of components available in eSIM. So wait. So library, and then sub-circuit library. So yeah, so we are increasing the components, so you can see the number of ICs available currently, and it's right now we have a good number of ICs, so you can try them out over here. And even though these are not available in the 2.5, this will be made available in 2.6. You can download if you need something. You can come here to this link and download the IC and try it out. If you face some issues or some problems, then please reach out to us. We will try this way. We will be able to improve in case there are some issues. Okay, so these are developed by the interns and students who work under the FOSSI team. Okay, so yeah, please do try these sub-circuit libraries. Okay, so any queries up till now? Any doubts, any queries? Are you there? Any suggestions from your side that you want us to try and show you? Any suggestions from your side? Okay. Thank you, Kalpana madam, and feel free to contribute. We need people like you to come up and help us in developing the tool chain and maintaining it, obviously.
So, Sumanto, are we done? Should we move ahead with the concluding part?
Yeah, we can do it. Anything else, people around? Any doubts? Okay, thank you all. Yeah.
Okay, so
I guess
Sumanto,
it's done.
let me interact with them, with the faculty members, and let me show a small presentation to them. And then once I'm done, you can just show them the website and talk to them and inform them how they can contribute to the eSIM project of FOSSI.
Sure, ma'am.
Okay. So, hello everybody. Very good evening to all of you. I am Payal Mukherjee from FOSSI IT Bombay. I'm working as a senior project manager here, and I'm really glad to see your enthusiasm and and the way you interacted with the FOSSI team. And just let me know a thumbs up. I mean, I need to know how you felt about the about this faculty development program as a whole. If you liked it, just a thumbs up for all of us. We'll also provide you feedback forms, but for the time being, just to say thank you to our team and just to show your enthusiasm, all of you who have liked this program, could you please show us a thumbs up? Okay, Mr. Bhaskar Patnaik has a question. Thank you so much, Dr. Dipti and Professor Shraddha, Professor Aarti. Thanks a lot. Thanks a lot. Yes, Professor Bhaskar Patnaik, you can just go ahead. You can unmute yourself and talk to us. If not, then let us take a break from this and let me show you a presentation. And after I'm done, you can again we can open the floor for interaction. Okay, so I'm just presenting my screen. Okay, am I mean, is my screen visible?
Yes,
Yes,
ma'am.
yes.
Okay,
But you can close this PIP window.
okay, fine. This one, right?
All right.
Okay, fine. So rather than a concluding session or rather than a conclusion, I would like to call this a new beginning for all of you. All of you who are attending this faculty development program, please consider this as a new beginning rather than a conclusion of this session. And just after this session, you will be getting to know about a number of opportunities through which you can connect to us and you can contribute and develop yourself, develop your students, and develop your institution, the institution where you are working in. Okay, so this opportunity actually, it's a bunch of opportunities by which you can develop your students, first of all, and then you can develop yourselves and your institutions. And how exactly you can do this, I'll just come to it. Okay, so is my second slide visible? Let me just confirm because Vinita
Yes,
was having
yes.
a problem.
Yes.
Okay, fine. Okay, so first of all, let me tell you that FOSSI IT Bombay provides an excellent platform for the faculty members to develop themselves through connectivity. So first of all, the faculty members can be connected to the students not only from their institute, but actually FOSSI has a huge base of students who come to us for internships, for workshops, for hackathons, marathons, etc. So we have a huge base of students to whom you can connect to. This is number one opportunity. The second opportunity is you can get connected to your academic peer community. There is a scope of cross-disciplinary collaboration, cross-departmental, cross-specialization collaboration with the academic peer community, because FOSSI has a number of other verticals apart from EE, and FOSSI actually has a number of faculty members who are connected to us. We call them faculty partners, and we have faculty partners from many academic streams. For example, we have faculty partners from chemical, from mechanical, from aerospace. Okay, and if you are connected to us, you can eventually be connected to our faculty community, the people who are connected to us. And then that is why we say that FOSSI is an excellent platform of collaboration within the faculty community. So this is an excellent platform that FOSSI IT Bombay is providing you. And the third thing is we also have a industry partner community. So it is very much good for the faculty community who are looking forward to enrich their research, who are looking forward to work with the industry people, and collaborate, and there is a opportunity of knowledge transfer, which is very important for our nation, for any nation. I would rather say that is very much important for any economy to grow, for any country to grow as per the academics and industrialization is involved. So there is a opportunity to opportunity for knowledge transfer between the academia as well as the industry of India through FOSSI. Okay, and you can also directly contribute to the core technical team of FOSSI IT Bombay eSIM team, because as you know, eSIM is developed by FOSSI IT Bombay, and we are in a process of continuous development of eSIM at FOSSI. So if you acquire the knowledge of eSIM, and if you are capable of contributing in some domain expertise, in some in some aspects of developing eSIM, you are most welcome to to connect to us and to contribute through the domain knowledge that you have. And all these things, all these collaborations and all these contributions will eventually add to one person's development, and that person is you yourself. Because while teaching the students, or while communicating with the academic and industry peers, and also the eSIM team of FOSSI, you are actually upskilling yourself. You're also increasing your visibility in front of the student, in front of the academic community, and in front of the industry. And you have, and in this way you are also escalating your network opportunities, the opportunities for networking. And as you know, networking is the net worth nowadays, and it's a very very what should I say, very important um, aspect of self development, and the development of your careers. So, and all these things will eventually add on to your academic credential, the value addition to your academics. So now this connectivity, collaboration, and value addition is actually a cycle. Okay. So if you are upskilling, if you are upskilled with all these connections that I mentioned in my last slide, you are upskilling yourself, and eventually you are passing on this knowledge to the students of your institute. And not only the students, you can also share this knowledge with your peers, and eventually you can develop your institution and the domain level, the knowledge level of your students and faculty peers, and your institution. And in this way, you can connect to FOSSI IT Bombay, and you can collaborate with us. And that will lead to the value addition of your institution. The ranking will go up. So I'll just tell you how. I'll just in my next slides, I'll talk about the details of how you can actually do this. So first, let me talk about upskilling your students. So this is a very much important arena where you can showcase your knowledge level. You can organize orientation sessions for your students, for your peer community in your in your institutions, and we are there to help you out. We will be present online whenever you are organizing these orientation sessions. We will be there. Our team will be there. We will contact your we will connect to your students, and provide them with all the relevant informations. Number two, the second thing that you can do is include eSIM in your course curriculum. Okay, so I can understand that the course curriculum is not set for a college which comes under some university. So in that case, please connect us to your HOD, to your director, and we can also be connected to the VC, or to the people from from your university. We can talk to them, we can have meetings, and eventually we can actually bring eSIM to your course curriculum, so that you can teach eSIM in your own classrooms, in your classes, as a part of your course curriculum. And if that not is possible, and if that is not possible, I mean, this including in your course curriculum right away is not possible. I know that most of the institutions have something known as value added courses. So you can have eSIM, you can teach eSIM to the students through FOSSI as a part of the course curriculum through the value added courses. So for another vertical of FOSSI known as Open which is used for the computational fluid dynamics stream for mechanical, chemical, aerospace branch of engineering, they have actually taught the students. I'll just name one institution. The name of the institution is VIT Vellore. So they have taught Open to their students as a part of the value added course. And this course was given to bachelor's level students, masters, and as well as the PhD level students. Okay, so this is an option. And also you can include eSIM in your lab courses. Okay, and in this way you can upskill your students. You can actually make them atmanirbhar, which is the in thing now. for all the students and faculty members. So if your student is Atmanirbhar in terms of software usage, your student is not, it is not mandatory for a student to look for jobs in only MNCs or in only the companies that are using, high and expensive proprietary software. Okay, and I mean, the students will be free to apply to any MSME. The student will be free to launch their own startups. So even if they are not getting employed in a very top-notch companies, other doors will be open for them. Okay, and this is only possible through the knowledge of free and open source software like eSim. Okay, so this is another thing that you can help the students with. The next thing, you can equip them with the knowledge of applying to internships and higher education. Okay, so internships not only in FOSSI, some in some other company or other institutions. Okay, and also for the students who are looking forward to pursue career in academics and who are planning to apply for higher education, then also you can help them with the knowledge of FOSS. Okay, so and the another thing that I want to talk about is the guidance part for the FOSSI interns. So if you are feeling confident that you know eSIM and you know how to apply eSIM and you are confident that you can guide the FOSSI interns and fellows, please write to us. We'll be happy to connect to you so that you can guide the FOSSI interns from the next semester. And all these things will eventually add value to your institutions. The ranking of your institution will go up, the NIRF ranking, because FOSSI is in line with CEP, this new education policy, NEP. Okay, and this, when your rank goes up, the admission will it will lead to higher admission and expansion of your institution. Okay, and that will eventually develop in the the holistic development of your institutions. And the other point is that my colleague Vinita told during her inaugural speech that if this funding of buying expensive proprietary software, the licenses of the expensive proprietary software is saved here, that funding could be diverted to other developmental activities of your institution. This is a very important thing because all of us loves to save money, and when it comes to large scale savings, it is actually very effective. And okay, so once you do all this, there is an opportunity to work with FOSSI directly as FOSSI centers. Okay, and once you become a FOSSI center, you can be present on FOSSI.in. And because FOSSI is funded by the Ministry of Education, Government of India, it is a very prestigious platform to have your colleges listed under the FOSSI centers in our website. So here I'll stop sharing, and I would request Sumanto to please take the audience to our website and talk about how can they actually take part in the eSIM projects. I mean, the projects that are available for the students, the projects that are available for the faculty, and everything that they can do with us after this program.
Yeah, thank you, Payal ma'am, for the concluding talk and presentation, briefing about the various things which the faculty members can do.
Yeah.
So, yeah, let me share my screen again. Yeah, so I had already talked some of the things. So the various projects which one can contribute, the faculty members can contribute are, so one can just check the home page first of all and what all activities we are doing. So research migration project, as I said, take up a paper from some from some from some website, a reputed journal, and try to replicate the same in using eSIM. And yeah, so and you will receive recognition on our website and a certificate from our team. Okay, and sometimes if your work is good enough, we can even give you honorarium. So yeah. We also have a circuit simulation project similar to this research migration project, where you are free to take any circuit, but you need to ensure that it's not available already on our portal. Then textbook companion, we had stopped currently since we weren't receiving enough textbooks. But yeah, if we have interested faculty members, then definitely. So it's about trying out examples using eSIM So for example, take up a textbook, for example, BL Theresa, take up a textbook and try out each and every examples using eSim, and submit the files, project files to us, and yeah, you will get a recognition on our website and a certificate. Similarly, we have lab migration project. So yeah, so the faculty members need to take. So while research migration, circuit simulation, and textbook companion can be done by anyone, lab migration is focused mainly for faculty members, the academicians who take up practicals in their institutes, so they need to they need to try out various labs, for example, digital circuit design lab using eSIM, and yeah, submit those files to our portal. You can even try out for the eSIM marathon I already talked about, and get a chance to get a chip fabricated by the open source shuttle programs which are funded by Google, Skywater, IHP, and so on. Okay, or at a very low cost. We also have internships and fellowships opportunities. So just for the research migration, we have around 250 plus circuits already submitted by different people, you can see. So some of your institutes may also be listed over here. So yeah, so please do motivate your students to apply here, to try this out. We have this circuit simulation project, so completed circuits. Okay, and yeah, so there are a lot of circuits available. So as Maheshwari madam talked, so there are 100 plus circuits already submitted from her team from VIT Chennai when she was a professor there. Okay, so and similarly lab migration project, we have around 9 labs, okay, on different topics. So feel free to submit more. And textbook companion, it has been closed, but on your request, we would like to open it again, maybe. So you can see the different labs, different textbooks. So linear integrated circuits by D. Roy Chaudhuri. So I would I want a thumbs up who use D. Roy Chaudhuri in their curriculum, in their colleges for teaching students, or maybe Donald Neiman. Neiman, many people will be using, I guess. Okay, nice. Yeah, so one can contribute over here. And yeah, then we also have Malvino, A.P. Leach, Malvino, so very famous books, and Mohammad Rasid, and so on. Yeah, B.L. Tharija. So yeah, so more books can be contributed, and yeah. So now from the developmental point of view, so this is the eSIM repository. Okay, so you can open up issues over here. So for example, if a professor is working in RF and he wants something, so just feel free to come here on this website and say that I need the RF components to be added to eSIM, or maybe power electronics components to be added in eSIM, and just create a well documented issue, so that maybe we can have interns. You can even have your own interns and your own students maybe may take up some projects, final year projects or something, and submit and create a pull request, and try to find a solution to the toolchain and create a pull request over here. And due to the advent of AI, I would say that understanding the code is not very difficult. One can easily do it. So one can try to understand the code a bit and create a pull request on our page and contribute to the library and the code base of eSIM. Okay, we are also developing KiCad plugins. Let me check. KiCad plugins. So this is something new. So there are different PCB plugins, different things getting developed, and people and the students are also writing papers. So your team can you can ask some students to create a KiCad plugin and create a PR on our repository, and we will accept it. And you can write a paper maybe on the same. So in similar manner, you can contribute, and once you have contributed enough to our uh, to our uh, to our to our project. So you can be one of us. For example, we have partners as so you can be one of the people listed over here. Okay, so faculty partners and industry partners. Okay, and yeah, for example, Maheshwari madam has contributed a lot. So yeah, you can even have a chance to win FOSSI awards, which Maheshwari madam has already shown in her presentation. Okay, so let eSIM project not be focused only with FOSSI. Let it be a community project. Let people, let faculties like you all also contribute and be a part of our team. And yeah, and for example, we need more people like Maheshwari madam who can contribute more. And yeah, so yeah, hope to have you all in the next faculty development program. So most of the hands-on sessions were done by me, Shanti, and Varat. So in next sessions, we hope to see outside people as well contributing who are apart from the FOSSI team, eSIM team. Okay, contributing to the eSIM FDP. Okay. So yeah, so thank you. Let's be in touch and
So,
let's
Monica, may I
contribute.
just propose the vote of
Yeah,
thanks once we
sure,
conclude
sure,
formally? Okay,
sure,
and
sure.
before that, let me just ask them whether they have any questions. So, anybody, if you have any questions for us, we are there to answer.
Any feedback? Someone
Yeah,
wants to unmute and say something?
yeah, any kind of feedback, positive and negative, because both are equally important for us to develop
Yeah.
ourselves as the eSIM team of FOSSI.
So yeah, just feel free to unmute. Just let us
Yeah,
know. Feel free to unmute and say
you can
whatever
unmute
you want.
yourselves. You can also, chat. You can take the help of a chat box to type your queries. And before we all leave, we want to have a group photo together. Okay, so all thank you messages, no negative
Yeah.
feedback for us.
Uh-huh.
Because I always look forward to it, because only then we can improve. We can improve and we can add things. We will try to add things which we couldn't add.
Someone said that we could have had this session could have been for 2 more days. Yeah, so we
Okay,
have taken it into account so that
okay, that is a very good feedback. So next
yeah,
time we will plan like that.
yeah,
Okay, so while we talk,
yeah.
and
So
offline,
there is one question for
offline would be
when we will have
possible.
FDP.
One second, Bharat. So somebody has requested for offline workshop. So offline is only possible at your institutions. If you call other institutions to your place, to your institution, and you fund our travel and stay, then more specialized and offline workshop will be possible.
Professor Avinash, do you want to say anything?
Yes, sir.
Yeah, please.
First of all, I am very much thankful to all the experts for delivering a nice session. All the sessions were quite informative, and also I'm thankful to Shashank Sumantokar sir and Varat Patil sir for their kind cooperation. Sir, one small suggestion from my end, that what happened is, it was, I felt it is too much hectic, that since morning 10:30 to evening 5:15 something, that timing is off. So little bit time you could have given us for practicing, because being a doctor, for first time I am using this eSIM in my curriculum. And because of, sir, what happens is, we can't tell anything because being in the professional field, but still little bit time could have given for practicing and all, some time in between, because I felt it is too much hectic. So it could have extended for another 2 more days the same program. It could have become more uh, uh, I think it's already informative, sir, but become help. It could help us the purpose for what we attended this.
Fine.
Yeah,
So
taken into
thanks
account,
for
we
this
will take
feedback.
those.
We take this feedback and we'll keep in mind, and for the next sessions we will plan accordingly.
Yeah.
Thank you, sir. Thank you, sir.
So just let me propose the vote of thanks to formally close the session. So first of all, let me thank IIT Bombay for providing all the opportunity that we are having here to take this project forward and delivering these kind of programs for you all. So thanks to IIT Bombay, thanks to the Ministry of Education, Government of India for funding this project. Thanks to NME ICT, the mission for which we are working here. Thanks to our principal investigator, Professor Prabhu Ramachandran, for all his guidance. Thanks to Dr. Maheshwari and all the other faculty members who have participated in this faculty development program as speakers during the lecture session. I'm thankful to Professor Sangeeta Mangesh, Dr. Inderjit Singh Dhanjal, Mr. Steve Hoover, Professor Rakesh Sinha, Mr. Vipul Sharma, Professor Maurina Ghosh, Mr. Latik, and obviously I'm really thankful to the eSim team of FOSSI. Applaud for the team members. The team lead is Mr. Sumantukar and Varad Patil and Shanti Priya. Shanti Priya, could you please switch on your video so that everybody can see you? You have put a lot of effort. So the entire eSim team has put a lot of effort towards this faculty development program, and that's why we were very keen for your feedback, because it's the first time that IIT Bombay is offering this program for the faculty members. We keep on doing workshops for the students, but for faculties is the first time. And the main reason for holding this faculty development program is, I believe that the faculty are the pillars or the channels through which we can reach out to the students with a very sound domain knowledge. And one faculty actually can develop tens and hundreds and thousands of students. Like, one faculty is capable of doing this. That is why we have tried to reach out to thousands of faculty members, so that they can be empowered and by the knowledge, by the eSIM knowledge, and they can train more and more students so that they can eventually give back to the system, to the education system, in this process. And I would also like to thank Mr. Deepak and Mr. Kailash from the studio team of FOSSI, and Ms. Preeti for all the logistics and professional efforts that she has put. And obviously, I'm thankful to my colleagues, Ms. Usha Vishwanathan and Ms. Vinita Gabri, for their guidance. Okay, so thanks a lot. And we are always there through email for any, for answering your queries, for interacting with you. And the eSIM team is a very active team, so you can expect replies within 24 hours. Okay, so I hope we can conclude the session here. Fine, we are done. Okay.
So photo we
Oh
will be
yes,
taking.
yes. A group photo. Yes.
Also, thank you to you for organizing this panel.
Yeah, my pleasure. And I would like to request all the participants to please switch on the camera so that we can have a nice group photo. We want to retain the memory here of our first eSIM faculty development program. Thank you, Dr. Dipti. Professor Vivek, why did you switch it off again? Okay. So once you all are there on your cameras, Deepak can actually take a click, and Sumantu can also do actually.
How many people have opened up the cameras?
I can only see Professor Bhaskar and Dr. Dipti. I would really request you to kindly switch on your video. You can take a couple of minutes to,
If you need some time, then just message in the chat box. Okay, it will be great. Since it's
Dr. Dipti, your daughter can come in, no problem. They are actually very curious. Okay, there are 74 people, and I can see only 3-4 people who have switched on their videos. Please switch on your cameras because we want to hold this memory.
खुल गया यार.
Okay. Are we ready?
I will take the screenshot count of 3. Okay.
Okay.
Be ready. 1, 2, and 3. One more, please. Just a minute. 1, 2, 3. Thank you.
Yeah. Thanks, Deepak. Bye bye, everybody. Yeah. Good evening.
Bye. Take care.
Bye bye.
Be in touch.
Thank you, everyone.
Thank you.
Thank you.